Well, so in average switch model, what we have done, we have obtained the linearized model of switch and diode, then replaced them in the original variable structure systems, then derived various transfer functions. Now, these transfer functions, which depicts the original physical system, has been obtained in mathematical form, right? Either in transfer function form or in time domain form, linearized time domain form. Right, so we have seen that using the both the methods, the transfer function obtained is same. Now we have also seen the comparison of the frequency domain response and time domain response in case of ideal DC to DC converter and non-ideal DC to DC converter. Then we found that the non-ideal DC to DC converter gives us more accurate information about the system rather than the uh, ideal DC to DC converter, and also the performance given by non-ideal transfer function was better, right, than the ideal transfer function. So that if we get the accurate information, then definitely our control efforts will be optimized, right? So it means one should get as far as possible the transfer function to be accurate one. Once now these transfer functions are obtained, then how to use them? Just a minute, please. Sorry for interruption. So once we have obtained these models, now how to use them for controller design, that we are going to see now. So why first we have seen why design is important for converters, that we have detailed discussion. Then why modeling was important, that we have discussed, that models is required because you want to control the uh, DC to, we want to regulate the DC to DC converters output voltage, right? So if we see earlier, we discussed that we desire that a DC to DC converter should have good line regulation, good load regulation. Okay, third, better transient response. and the fourth one is it should be stable, right? Now, good line regulation, good load regulations, all these is required. So we have also seen during the design process that these converters have, let's say, known idealities, right? Due to which voltage gets dropped and output voltage is not as the desired. So then what we need to do? We need to increase the duty cycle in order to meet the losses or voltage drops due to non-idealities. Then we can get the actual voltage. That's what we needed, right? So as if we increase the duty cycle, we get the desired output voltage. Now, if it is, let's say this was the just internal loss which we could calculate it and increase the duty cycle. But if this is due to the variation in input voltage, it is due to variation in load, then how to do it? So for that purpose, we have to go for closed loop control. We have to go for closed loop control. Now, for closed loop control, when we go, then how does it work? That we will see. Let's say this is a buck converter where input voltage is 20, output voltage is 10 volt. So for that purpose, my duty cycle here will be 0.5, right? So let us consider ideal voltage. It will be giving 20 into 0.5, 10 voltage. Now, due to some reason, if my voltage becomes 22 volt, okay, so duty cycle is 0.5, then output will be 11 volt. Output will be 11 volt. So that is not the desired, right? 11 volt is not desired. Desired output voltage was 10 volt, but it has increased to 11 volt. Why? Because there is an increase in the input voltage, right? Now, but we want to regulate it to 10 volt, right? Similarly, let's say the voltage is dropped to 18 volt, right? But duty cycle is 0.5, so output voltage will drop to 9 volt. But I wanted to regulate output voltage to 10 volt, despite there is variation in the input side. So what is the possibility, right? So if it is 18 volt, duty cycle is 0.5 and output is coming 9, but I want it to be 10, right? So what I can do, I can increase this duty cycle to such that this 10 upon 18, 10 upon 18, that becomes duty cycle. So if I multiply this 18 with 10 upon 18, then output voltage is 10. So 10 upon 18 is obviously greater than 0.5. It means if I increase the duty cycle when input voltage drops to 18 volt, then I will be able to obtain the 10 volt output. Similarly, when the input voltage 22 volt, duty cycle was 0.5, output has gone to 11 volt, but I want bake it to 10 volt. So what I can do, I can set this duty cycle to to 10 by 22. So definitely this is less than 0.5. It means if I reduce duty cycle from 0.5 to less than 0.5, that is 10 upon 22, then this voltage will be tracked to again 10 volt. Right, so this is some figures which I have given you: 18 volt, 20 volt, 22 volt, but it could be somewhat else also, 19 volt, 19.2 volt, like that. So if this is varying arbitrarily, obviously within the range input side, then duty cycle also should vary in order to regulate the output voltage to 10 volt. So who will do this function? Who will do this function? Who will moderate the duty cycle? So for that purpose, we close the feedback loop and then do the calculations, right? So what we do, we sense the voltage from here. Obviously, if this voltage is very high, then what we do, we use some voltage sensor here, voltage sensor. So this voltage sensor uh, do two jobs. Voltage sensor, this voltage sensor performs two jobs. One, it provides isolation. Do second, it does scaling, scale down, right? So the controller part which we are having is of low voltage. low power circuit, right? So what we do, if this voltage is 100 volt, 1000 volt, something like that, so we cannot feed directly this 1000 volt to our controller, right? So we have to reduce this control voltage, this output voltage, such that it becomes within the range of controllers. That's 10 15 volt, like that only. But if it is 10 15 volt itself, then we can directly feed it. Okay, but in simulation you can feed it directly, not an issue. But in experiments hardware, you have to do it through voltage sensor, right? Now this output voltage is measured here, brought it here, then we have some reference voltage, right? So if reference voltage, so let's say this is some 1 by beta times you are doing, gain of this voltage sensor is 1 by beta, then what you have to do, you have to do this also 1 by beta, some v naught reference. So for now we are considering just beta is 1, so we output reference is same. Now this actual voltage we are comparing with the reference voltage, and reference voltage is the desired voltage. So this is positive sign, this is negative sign, so there will be an error. Now this error is fed to a controller. Just we consider to a controller. This controller can be any controller, right? To a controller, which in turns gives a modulating signal. This is called control signal or modulating signal. Modulating signal. Now this modulating signal is compared with a short-tooth waveform, right? I will discuss in detail what is this. Is compared with a short-tooth waveform, which in turn generate the pulses, and these pulses are given to switch, right? So before giving this, we use a driver circuit. We use a driver circuit. Now the purpose of this driver circuit is again two. One is it provides isolation, right? Second, it provides amplification. Amplification. So this pulses, so this entire part, this is part of controller. This is part of controller, right? And rest of the part is called power circuit, which is our hardware power circuit. So we want the isolation between power circuit and control circuit. Power circuit and control circuit. So there is two way of concept of power circuit and control circuit. One is this pulses are interacting. Second is this voltage is being sensed. So in both the places we provide, it is better if we provide the isolation. So if we provide the isolation and if there is any fault on the power circuit, then definitely it will not enter into our control circuit and it will not damage to this. That is the purpose of isolation, right? Now how does this work? Let us see. Okay, how does this work? So for now, just I'm deleting this entire thing. Okay. Well, so let's say our voltage is 22 volt. It has increased to 22 volt, and duty cycle earlier was 0.5. Output voltage become 11 volt. Now we want it to 10 volt. So what we should do? So this 11 volt is being feedback, and its reference voltage is 10 volt. So what will be error? Error will be -1 volt. This -1 volt error will be there. Now whatever earlier value of VC was there, so this error will be fed to PI controller, and this whatever signal was coming from PI controller earlier, that will reduce due to this minus error. Now this signal will reduce. Now this signal will reduce. In turn, this will reduce this duty cycle, and that's what we wanted, right? That our duty cycle should reduce to 10 by 22. So in multiple, like 2-3 cycles, this will reduce and the output voltage will be brought back to 10 volt. Similarly, if it was 9 volt, if it was 9 volt, then this 9 volt would be sensed here. Comparison will be taken. Now this is a error of plus 1 volt. Now this error is fed to PI controller because error is positive. So whatever signal was available here, that's corresponding to 0.5, that will now increase. Now this signal increase, due to which the pulse width of the pulses will increase. Now this increased pulse width will derive this MOSFET, and because duty cycle has increased, so now this 9 volt will increase to 10 volt in few cycles. That's how this controller does works, right? Now here we have few uh, sections, right? So just one section is this power circuit, right? One section is power circuit. Another section is this PWM modular, and the third section is this controller, right? So we can represent this in terms of block diagram. We can represent this in terms of block diagram. So you can see here, just you can see, we will come back here. We can so this was our figure. So we can represent this in terms of block diagram. So this model we have already obtained, right? So what is the things here? This is duty cycle here. This is output voltage here. Now this output voltage is being fed. So we have this VC here, then duty cycle, right? So if we do its, we draw its block diagram, then this is our converter, which is giving us a relationship between V node and D that we have already derived. So that is a transfer function of DC to DC converter. So modeling part we have already done, right? Now this V node is changed. So V node is changed, and obviously if we have any sensor here, then sensor gain HS will come here. Otherwise it will be 1. So for now we are considering this to be 1. Now this voltage is reaching here. This voltage is reaching here. Now this is compared with the reference. This is compared with the reference. Now error is there. Now this error is fed to PI controller or any controller, right? Now this controller's output is VC. So this is VC. Now this VC is given to this PWM modulator, within which it is compared with a fixed frequency short-tooth waveform. So this is compared within the PWM modulator, and this modulator gives a duty cycle D. This modulator gives a duty cycle D. So this duty cycle D is here. Now this D is given to this switch, and like that this block diagram is there. Now within this block diagram we have this buck converter with us. This is already done. Now if I can obtain the relationship between B, C, and D, then this is known to me, this is known to me. If both are known to me, then I can design. Now this is the only controller part which is unknown to me, so I can easily design this controller part, right? I can easily design this controller part. That's what we will do. Now in DC to DC converters, normally we design the controller using frequency domain approach, because this converter is subjected to high switching frequency, right? So switching frequency is one of the key parameter which we have to keep into our mind, and based upon that, if we design a controller, then it will work fine, right? So before modeling, before designing a controller, let us see some fundamentals of controller which will be required. Which will be required. So before that, we were just discussing this block, right? This block. So I am rewriting this PWM modulator again here. We need to get the transfer function of this PWM modulator. So what is this PWM modulator? There is a signal VC to this at positive terminal, and there is one more signal to this, which is short-tooth waveform, fixed frequency short-tooth waveform. And the comparison of both gives us the pulses, right? So let us see here in big picture. So let us say this is our short-tooth waveform, which is having magnitude, let's say Vm. Its magnitude is Vm, this is 0, and this is T, this is 2T. It means this period T, which is equal to 1 upon Fs, Ts you can say, T you say, just T you say, simplify it, which is equal to 1 upon Fs, and F is switching frequency here. F is switching frequency, right? Now we have, this is VC with us. We have DC with us, right? Now these two are compared, right? So the logic here, the logic which works here, that if VC is greater than, so what I should say, this to be VT, triangular waveform or short-tooth waveform. So if VC is greater than VT, then output is 1. If VC is less than VT, then output is 0. Right? That is the logic. So here VC is greater than VT, so our pulses will be like this, because we will compare from here. Right? So this is the pulse width. Huh? Now if VC gets increased, so let's say VC gets increased with another color, yellow. So your VC gets increased, let's say. So now what will be the pulses? So I just draw with corresponding to this. So new pulses will be according to this. So now you can see here the pulse width have also increased. Now let us say VC could was decreased. So VC, let's say it was decreased to some value of this, right? Then it is crossing here only. So what is our pulses? Like this. So what we are seeing, if VC is increasing, our duty cycle is increasing. If VC is decreasing, then duty cycle is decreasing, right? So if we control the VC, and VC is what? Modulating signal here, modulating signal. So this modulating signal will depend upon, because this controller, once, like if we say the fixed controller, so once its parameter is tuned, it is fixed. Now depending upon error, its output will change, right? Now we want to find the transfer function. So this is D, this is VC, and this is, let's say, VT, right? So we will again draw it for simplification. Right, let's say like this. And this was our signal, right? So this is Vm, right? And this is time period T. Now this is Vc. It means this was Vm, and this distance is Vc, and this time is D into T, right? This time is D into T because it is the duty cycle. So on period is the D into T, and you can also do the pulse over here. So This was our pulse, right? So now these two triangles are there with us, right? I highlight this. One is this one. One is this one. Another is this one, right? So in these two triangles, let's say we name it O, A, B and O, A, B. So this angle remains common. So in triangle AOB and triangle AOB, right? Theta remains same. So we can say tan theta. Tan theta is this height which is VC upon base. So that is D into T should be equal to this height Vm upon base, which is T. So from here T will cancel out. So we get D upon Vc equal to 1 upon Vm. It means duty cycle is 1 upon Vm into Vc. So if you have Vc, you multiply this with 1 upon Vm, you will get the duty cycle. So this block can be represented as likewise. Here you have 1 upon M, this is Vc, this is duty cycle, right? So we can represent this block Vc means this PWM modulator. We can represent like this. So here if you see this PWM modulator, which is Vc into 1 upon Vm into D. So here now depending upon performance, we want to find the parameters of PI controller, right? So this is buck converter transfer function, which is already known to us using the any method, state space averaging. So this is a generalized form. Let's say I've written for buck converter. Now this PWM modulator transfer function 1 upon Vm or Vsw, which is one of the same thing. You can write Vm also or Vsw, which is the peak of sawtooth waveform. That is known to us. Now only part is unknown to us is PI controller. PI controller. So this is a transfer function of PI controller. So how to tune these parameters based upon given performance specification, that is our target, right? So what we have seen yesterday, that this was the transfer function. Transfer functions V node upon D is Bode plot. So what we are observing here in this Bode plot, let us consider we are taking this non-ideal one only. Here, this DC gain of the, so this is called Bode plot, right? So Bode plot is nothing but it's a simple transfer function is there. So if I describe transfer function is there. In transfer function we put S equal to j omega, right? Then after putting S equal to j omega, we will get the another form of this transfer function. We will take its magnitude, we will take its angle. Then these magnitudes and angle at different frequencies we will plot. So at every frequency we will have certain magnitude, every frequency we will have certain phase angle. So for by varying the frequency from 0 to infinite, we can have various pairs combination of these magnitudes and phase angles. When we plot such magnitude and phase angles, then we get the Bode plot, right? And this is because this magnitude may be very large. So in order to represent them, we represent this in dB. We take 20 log of that particular amplitude, right? In decimal representation, then we represent it to dB, right? That is magnitude, and phase angle is in degree. So this representation gives us Bode plot. Now Bode plot has four important parameters: gain, crossover frequency, phase crossover frequency, gain margin, phase margin. Now these phase crossover frequency, gain crossover frequency, phase margin, gain margin, DC gain, these are the specifications which uh, decides that how system will behave, right? And So this is the Bode plot of frequency response of open loop system, right? Now we are designing a controller. We are cascading a controller with this. It means we want to reshape this frequency response, right? So something is missing here, or some performance specifications are not meeting here. So to meet those performance specifications, we are adding something which is called controller, right? So what is missing here? First, let us analyze that. Before that, I will just brief what is the phase crossover frequency, gain crossover frequency, like that, right? So I have written this definition for you. For a stable system, how to do stability analysis using Bode plots, right? So from the Bode plots, we can say whether the control system is stable, marginally stable, or unstable based on the values of these parameters, right? So these four things are gain crossover frequency, phase crossover frequency, gain margin, and phase margin. So what is this? So I'm just drawing one plot over here. Let's say I'm just plotting here itself. So this is 1 minus 80 degree angle. This is G dB. This is 0 dB. This is just magnitude. This is magnitude. This is 0 dB. And then let's say this is its Bode plot. Right? So this frequency at which this magnitude plot. So this is called magnitude plot. Magnitude plot. Frequency at which this magnitude plot crosses the 0 dB line, that is called gain crossover frequency. So the 0 dB line is equivalent to absolute 1, right? So this frequency at which this magnitude plot crosses the 0 dB line is called gain crossover frequency, right? And the frequency at which this phase plot, this phase plot crosses the minus 180 degree line is called phase crossover frequency, omega pc, phase crossover frequency, and this is gain crossover frequency, right? Now we have defined some two more specifications. So let us first understand one by one. Phase crossover frequency. So the frequency at which the phase plot is having the phase of 1 minus 80 degree is known as phase crossover frequency. It is denoted by omega pc. The unit of phase crossover frequency is radian per second. Now this phase crossover frequency at this, okay, and what is the gain crossover frequency? The frequency at which the magnitude plot is having the magnitude of unity or 0 dB is known as gain crossover frequency, right? It is denoted by omega gc. The unit of gain crossover frequency is radian per second. Now, interestingly, at this omega pc and omega gc, this system is having certain phase at omega gc at this frequency. This system will have certain phase, and similarly, this omega pc, this system will have certain gain, right? So we will measure what is the gain below this, right? What is this gain, right? And similarly, we measure that how much is the distance of this phase from minus 180 degree line. So we call this to be positive phase margin and this to be positive gain margin, and we will see that in this case system is stable. In this case system is stable, right? So the stability of control system based on relationship between phase crossover frequency and gain crossover frequency is listed below. So who is coming first here? Omega gc, right? Omega gc is less than omega pc. So gain crossover frequency is less than phase crossover frequency, in this case system is stable, right? Omega GC is less than omega PC, so system is stable. And another example I can take, let us say one more example with some another color. Okay, so this is magnitude plot. This is phase plot, right? This is minus 180 degree line. And let us say this is your omega GC, right? And this is your omega PC, phase crossover frequency, right? So at this phase crossover frequency, this gain is there, but this is called negative gain margin. And at this omega GC, phase is there, but this is below minus 180 degrees. So this is also negative phase margin. Here phase margin and gain margin both are negative, and this system is called unstable. This system is called unstable. So here what we can see that omega PC is less than omega GC. Omega PC is less than omega GC, and there can be a chance where both are same kind of like, let's say this could have been moved from here. So in this case both are same, omega GC and omega PC, right? So in that case system is called to be marginally stable, right? Marginally stable. So this omega PC equal to omega GC, then control system is marginally stable. Omega PC is less than omega GC, then control system is unstable. So what is our target? That when we design a control system, then our phase crossover frequency and gain crossover frequency should be such that the system becomes stable, right? And gain margin, so gain margin, as I told, gain margin is the factor by which the gain of a system can be increased at phase crossover frequency to bring the system to the verge of instability. So this 1 upon GM, whatever this gain margin is 1 upon whatever this value, let's say this is A, so this A, right? Similarly, what is this phase margin? Minus 180 plus this phase, let's say this is 5 years, so 5 years, sorry, 180 plus this 5 years, that is the phase margin. Okay, so that way we can obtain phase margin and gain margin of a system. Okay, so for a converter, what should be this gain margin and phase margin? So the ideal gain phase margin for the converter should be greater than 50 degree, but obviously less than 80-90 degree, because more the phase margin is there, then lesser are the overshoot, right? But if phase margin is too much, then your system overshoot will be zero, but system will be overdamped, or it may be very sluggish, right? Similarly, when we choose the gain crossover frequency, then this is chosen as 1/10 to 1/5 of switching frequency. So these are the thumb rules by which we choose phase margin and gain crossover frequency for the GCF, gain crossover frequency for the DC to DC converters. And normally in DC to DC converters, we will see gain margin is infinite and this phase crossover frequency is also infinite. So we will take care of these things. One more thing is required, the DC gain. DC gain should be very high, or you can say it should have minus 20 dB per decade slope in magnitude plot of Bode plot, right? So here, here uh, in this, you will see that this is not having or this is having constant gain. So for step variation, this will be having the steady state error. If there is step variation in the input voltage, then it will be having steady state variation. So that's why our purpose is that this slope should be modeled such that here we have minus 20 dB per decade slope. That is our target, right? And this is positive phase margin. This is positive phase margin, but it is less, 26 degree only. So our target is that it should go somewhere 60, 70 degree. So if that is there, then these oscillations will not be there. These oscillations will not be there, and it will be reaching to steady state soon. So with these amps, we go ahead to design a controller, right? We go ahead to design a controller. Okay, so this concept I have told you. Yeah, this is a phase margin. I have told you the phase margin is the amount of phase lag that can be introduced into the system at the gain crossover frequency to bring the system to the verge of instability, right? The formula for phase margin is 180 degree plus 5 GC, as I told you. So the system stability can be defined as below based upon the relationship between gain margin and phase margin. If both are positive, phase margin and gain margin, then system is stable. If both gain margin and phase margin are equal to 0, then it is marginally stable. And if the gain margin and or the phase margin are negative, दोनों में से एक भी, out of two, if at least one is negative, then we say that our control system is unstable. So our target is that phase margin, gain margin, both should be positive, right? Both should be positive. And if it is positive, then also their value should be optimum enough so that we can get the desired performance, right? We can get desired performance. Now there are multiple ways to improve the performance of the system, right? So we have transient performance, we have steady state performance. Two types of performance we are having. So various controllers can be used. So before reaching to this PI controller, just see, we can have individually, like we had error here, this error is now being fed to the controller, then then it is fed to the VC, right? So let's say this error is coming to us. In general, if I talk about control, it is coming to us, then this error can be fed to a proportional controller, then its output is there, right? So this P controller KP, right? Then it may give you as a modulating signal. So this is called proportional controller. This improves the gain of the system. For example, let's say if this is your reference line, but system is having this much only. So what this will do, this will multiply the entire response with some factor, and like that it will shift up. Okay, like that it will shift up. If you multiply this entire by this difference, then entire will shift. Okay, so now what will happen? Your gain will increase, and also you will see that here your rise time will increase, right? But if you use the I controller ET, right? So here your error is being integrated and you are getting this output, let's say YT. So here your YT is simply KI ET DT. In this case, YT was just KP into ET. Now the third case, so this how this this is proportional, this is integral controller or I controller. So its transfer function is just ys upon es, that is kp only. Its transfer function will be ys upon es, that will be ki upon s, right? So it will help to improve steady state error. Steady state error. So why it improves the steady state error? Because it aids one pole at the origin. That's why it improves the steady state error. But because this is increasing the order of the system, right? That's why there is chance that stability of the control, stability of the closed loop system may decrease, right? May decrease. It increases the order of the system. That's why the stability of the controlled system may decrease. Now, one is T controller, ET, derivative controller. So this is KD, dy dt, yt. So yt equal to KD, dy dt, et, right? So from here, if you get ys upon es, that's comes out to be s into kd, s into kd, and this gives this helps, and because this s is in numerator, when it gets cascaded with the system, then it decreases the system's order, decreases system's order. So it decreases the system's order. So stability slightly may improve. Stability may improve. Moreover, due to this, what is happening? The system transient response improves because this is derivative, na? So this peak values gets decreased. It increases the damping. So this system's transient response improves. Transient response improves, right? But this D cannot be used alone, right? So the combination of these can be Kp. Normally the popular combinations which we do use are Pi and PID. So in Pi and PID case, if I take in general, this is the ET which is given. Now all are connected like this. Then these all three are together brought, added, and then this is your output. Like that this PI controller works, a PID controller works, and the transfer function becomes then Kp plus Ki upon S plus Kd up into S, right? So normally D we do not use, so in that case it is Kp plus Ki upon S, right? So that is your PI controller and PID controllers. Now how to tune these parameters, that we will see. So this is the PI controller which we need to tune. Now there are various approaches to tune these PI controllers. Like basic one, we have Ziegler-Nichols method, right? There are other methods also. So before we will be doing today one method which is called stability boundary locus methods. If we are given with a transfer function, then how to tune the Kp and Ki. Before that, we will see from something from experimental point of view, that how this closed loop system may be, uh, implemented in experimental work. So this is our experimental part, hardware buck converter or any converter. Now this, as I said, this is sensed through the sensor. So normally we do use this. So this is, yeah, this is our circuit is there. Okay, so this circuit is there. This circuit. Now we use voltage sensor from here and feed it back to our amplifier. So what we do, we take the actual output voltage, and this is the voltage transducer. It's from LEM LV20P. So what does it do? It provides the isolation between these two, and here we are feeding our actual voltage. So this is the current limiting resistor. Now this voltage is fed here. Now in turn, this voltage is scaled down based upon the whatever resistance ratio we do use here, and scale down voltage is obtained here at this terminal of this voltage sensor, and this voltage sensor is then this. Now this voltage you can sense and you can feed to your controller, that we will see. Similarly, we will see later on that if we are using current control, then we do use current transducers. And current transducers, what we do, we feed the actual current to this current transducers. It provides the isolation, and then it provides also the some gain scale down. It scale down this current, and the scale down current is obtained here. Now we obtained this current and multiply and pass this through certain non-resistance, then this current is transformed into equivalent voltage form. Right, now how to scale down this? So there are number of turns here, right? Many holes are there, so how many times you are taking the turns, based upon that it will be scaled down. So this is the scale down current we obtained. Right, now how to use this in, this is just one environment, MATLAB Summit environment plus DSpace, or you can use any DSP based processor as well. So this is the actually sensed output voltage, as I said you, right? Then we provide it to voltage sensor. Now this voltage sensor will reduce it to some value, so that you will select that what should be the scaled down ratio. So in my case it was 1/4, right? So I have scaled down it to 1/4. Then again I have given this is the analog voltage, right? This is the analog voltage. We have connected it on terminals of ADC channels of the DSpace, right? ADC channels of the DSpace. So here now in this DSpace, actually for the extra protection, this DSpace itself reduce this voltage to 1/10. They have their own scale down scheme, right? So whatever voltage you apply, that will be 1/10, right? So it is further 1/10. So actual voltage becomes 1/40, 1/40, right? So now this is given. Now it is processed. Now within the MATLAB, what we do, we have a DS110 ADC block that we select, and here the number of the number of the ADC channel at which our actual voltage is applied is put, right? Now this voltage, because we need actual voltage, so it was scaled down by two factors, 1/4 and 1/10. So we need to multiply this again by 4 and this by 10. So after multiplication we get this output voltage, right? Now this output voltage is compared with the reference output voltage. This is our reference output voltage, whatever we say, 20 volt or 10 volt, whatever. Now this is compared. Now this is your controller, which may be PI or PI lead. Now this controller value we will be tuning, right? We have already tuned, so that value will be put over here. So that controller is being done. Now this controller's output is VC. This is duty cycle limiter, just we have used in case if this value increases greater than 1, then it will be saturated to 1, or let's say somewhat less than 1, because 1 will just make the switch to be always on. So 0.9, right? So 0.99 somewhere we set this limit. Then in the MATLAB, there is a block which generates the PWM pulses and compares it with this signal. So this is called PWM slab DSP PWM generation block, DS110 slab DSP. So we could generate 20 kilohertz pulse for that. And now this pulse is given back to IO bits of the DSP. Now, these IO bits are available on the connector panel, external panels of the space, from where we can get these pulses. Now, these pulses which have been generated, they are of very low voltage, 3.3 volt or like that, right? But now our this the actual switch which is used here is MOSFET kind of switch, right? And that needs at least 12 volt to 15 volt pulse, at 12 volt to 15 volt pulse. And for that, this whatever uh, gate pulses are being generated here, that need to be amplified, amplified right? That need to be amplified and feed to this MOSFET and fed to this MOSFET, right? So that's why we use this driver circuit. As I said earlier, this driver circuit should provide amplification as well as isolation. And this voltage sensor also should provide the isolation, right? So this is how this is, uh, done in experimental work. We need sensors, we need these processor in which we need to implement, then our actual pulse will come, right? So what is the driver circuit that we will see? Driver circuit's purpose is amplification and isolation, right? So there are various ways to obtain this. So this is the pulse which is obtained from your processor, switching pulse of 3.3 volt or 5 volt, which is obtained from pulse. Now this is our MOSFET. This is our MOSFET, which is having three terminals. One is drain, another is source, one is gate. Three terminals are there. So D and S are power terminals, drain and source. So these three terminals, like I draw it back here. This is drain, this is source, this is gate, right? So this drain and source, they are connected to our circuit, main circuit, original circuit, power circuit. Now this gate and source, they are connected, or they are given the pulses, right? They are given the pulses. Based upon that, switch will be on and off, right? Based upon that duration for which switch will be on and off, and frequency also it will be decided by the pulses, right? So this voltage which is applied here at these terminals, that should be having magnitude of 12 volt to 15 volt, right? Depending upon different MOSFETs may have different ratings. So some may have 15 volt, 20 volt, 12 volt, like that, so that we can see from the data sheet of particular MOSFET, right? So now this pulse need to be amplified and need to be isolated. So we use one optocoupler over here. Sorry, this is applied over here, not here. This is applied at this point, gate signal input at this point, right? This 5 volt is used to derive this optocoupler IC, whose number is MCT2E. So MCT2E is a optocoupler IC which provides isolation. It is not providing amplification. It's optocoupler, so it provides isolation. Now this waveform, isolated waveform, so you can see signal A is our original waveform. Signal A is our original waveform, right? And which is applied here. Now based upon this transistor's function, this waveform at B is like that. It is inverted. Now this waveform of P is, this is a optocoupler here, this light emitting diode optocoupler. Based upon that, this transistor will be on and off, right? So based upon this transistor's operation, the pulses at point C is like this. Pulses at point C is like that. So this pulse and this pulse, you can see kind of similar pulse. The only difference is that they are isolated now, right? Now at this end, we need to apply the voltage, DC voltage of the same level which is required by the MOSFET, of the same level which is required by the MOSFET. So yes. So now let's say the voltage which is required by the MOSFET is 12 volt, right? So we need a 12 volt power supply for that, right? So first let us finish this one. We will see how to develop this 12 volt supply. So 12 volt supply, let's say we are giving it from anywhere, right? So now at D point, right? At D point you will see this is the pulse, right? Whose magnitude is now 12 volt. And if it is 15 volt, then the magnitude of these pulses would increase to 15 volt. So like that, we will be feeding now this pulse D, this pulse D to our MOSFETs. This pulse D to our MOSFETs. And yes, and then MOSFETs will be turned on and turned off. Now, if there is any change in the frequency or let's say the pulse width from this end, then there will be change in pulse width and magnitude at this end also. So in all these waveforms, what do you observe? That pulse width and frequency has not been changed. The magnitude might have changed, but if you compare this waveform and this waveform, then their pulse width and frequency has not changed. It is same. It is same, right? So that way we develop driver circuits, gate driver circuits, right? And what also we do need, this power supply. So this power supply directly we can use from DC power supply, or we can develop our, we have developed our own 12 volt power supply. So you can also easily develop your own 5 volt, 12 volt, 15 volt power supply, right? Now how to develop? We take the AC supply from AC mains 230 volt, then we use a transformer, right? So any transformer which gives from like 230 volt to let's say 15 volt. There are transformers which generate 15 volt, right? So accordingly the ratio is set. So they give 15 volt out of 230 volt. So this transformer is chosen in such a way that whatever voltage we need, so it's slightly higher than that. If it is 15, then we can go for 24 volt transformer like that. This transformer should be on higher end, slightly higher end. Now what we do, we use a rectifier circuit. So this was the sinusoidal waveform. Now we obtain the rectified waveform at these ends. Now this is not a DC, this is rectified waveform. So we use a capacitor, large capacitor of 1000 microfarad, and the rating is decided based upon the transformer rating. Now due to this capacitance, what will be happen? Most of the ripple will be taken out, and here we will be having rectified output only, right? Now this rectified output is fed to this regulator 7812. So there are various regulator ICs: 7812, 7805, 7809, 7815, 7818, like that, 7824, right? So this 78XX family, right? So 78 gives that it's a positive voltage, plus 12, plus 5, plus 9, like that, right? And this XX is the number of voltage. Similarly, we do have another IC set which is 79XX, 79. 05791279157924 like that. So this 79 represents negative voltage. Negative voltage. So here we need positive voltage only. So we have used a regulator 7812. So these are the linear regulators which we have already discussed in very starting classes of this converters. So this is a linear regulator. Now this regulator gives us a regulated voltage at these terminals of 12 volt, right? Because we are using 7812. Now again there may be some noise or some ripple. So again we use a capacitor, but of low voltage and low microfarads, right? So that capacitor has been used. Now this we consider that it's a kind of pure DC, right? And we feed it here, or that's how this power supply is made, and it is fed to driver circuit. Now instead of doing such big things, what we can do, we this I'm talking about the driver side. If driver side complications we have to reduce, then there are now ready-made ICs which can operate in kilohertz. Like one is TLP250, another is TLP350. 25 may be used up to 25 kilohertz. This 350 may be used up to 50 kilohertz, right? So here we are giving our gate pulses. Then this is the resistance which control the current, right? This also provides isolation. And here we need to connect if plus minus 15 volt power supply. So this plus minus, not plus minus, sorry, plus 15 volt power supply. So similar to this, we can use 7815 IC, and we can get the 15 volt DC, right? So this decides the level of output voltage, and this pulse now we what we obtained here. So this is isolated and amplified gate pulse for the MOSFET switch. So directly we provide these pulses to the MOSFET, and this 0.1 microfarad small capacitance is again used to filter out any noise present at the ICM, right? So what you can see here, only two steps. One is the gate pulses from your processor DSP, and this is the amplified pulses of desired magnitude, but having the same pulse width and same frequency, right? Now these pulses are given to your MOSFET, and if there is any change in the pulse width and frequency, that will be reflected, and your MOSFET will be operating and giving the desired output voltage. Okay, so this is how driver circuits are developed. Protection circuit, yes, we need protection also. So if we say protection of MOSFET, then we use snubber circuit. So this is the snubber circuit, right? And this is MOV, metal oxide varistor, metal oxide varistor, MOV. So what this MOV does, if there is high voltage applied across these terminal D and S due to some region, then this is having negative resistance characteristics kind of thing. So non-linear resistance characteristics. So high voltage is applied, then its resistance goes down. Its resistance goes down, and it provides a low path to that spike, and all the currents passes through this MOV, right? That is the first protection. Now another protection is we use snubber. We use snubber circuit. So snubber circuits helps us in protecting high dB by dt, high dB by dt, right? So the dB by dt protection it gives. So normally in MOSFETs we do not need it, right? But yes, if it is there, that is good. We can design it. Okay, so before moving to buck converter PI controller design, if you have any questions, please let me know. If so far you have any questions, please ask. No question. So we can have a break of a few minutes. Yeah? We can have break of 5 minutes over here. We'll continue then. Well, so now we will be designing the controller. So we do follow this, yeah, this block diagram. So I'll make it no issue. Yes. So let us make it there. Output voltage reference plus minus output voltage. This is our PI controller, right? This is our PWM modulator. This is our DC to DC converter. This is output voltage. This is feedback, right? Now we have this transfer function with us. GS equal to B1S plus V naught A2 S square plus A1S plus A naught. We have considered this to be in general form, right? Now in generalized form, and PWM pulse modulator transfer function was like this GPWM bars your 1 upon Vm. So let us say Vm is equal to 1. So this is 1. Now DC to DC converter transfer function is V naught upon D. Right? This is V naught upon D. Now this V naught upon D is known to us. This is GPS plant function. So now in cascade to both, this G equal to GP into G PWM. So that is 1 into this GP into 1. So this is GP itself, right? So your GS is our transfer function of buck converter, which is already obtained. Now we define this PI controller transfer function, right? PI controller transfer function. Now KP S plus K upon S. Now our target is to tune the KP and KI, right? Now how to tune? So now what is left with us? The GS is there, right? Then GCS is there. And this is your V output reference, and this is V output. Okay, so now the performance of our GS is we need to the performance of GS we need to improve, right? For that purpose, we are controlling GCS, right? Now the GCS is here. So what we are doing here, we are specifying a phase margin. Okay, one more thing I wanted to tell you that in this case, like here, if you see here, we have phase margin 26 degree, but gain margin is infinite. Why gain margin is infinite? Because gain margin is obtained at phase crossover frequency. So phase crossover frequency is the frequency at which phase plot crosses minus 180 degree. So phase crosses the minus 180 degree at nowhere. It means at infinite. So there is no crossover frequencies. So if crossover frequency is at infinite, then this also goes to infinite. So your margin also becomes infinite. So gain margin becomes infinite. Like that, we tune this PI controller only for phase margin only. We want to improve the phase margin, right? So we specify this phase margin to be 5 degree, gain margin to be 8 degree. A, magnitude A. So the characteristic equation, let's say we introduce this gain phase tester here, e raised to power A, e raised to power minus J5. This is the gain phase tester which we introduce here. Now what becomes our closed loop transfer function? Earlier it was 1 plus GS equal to 0. With controller it is this, and with gain phase tester it is A into e raised to power minus J5 GCS GPS equal to 0, right? So this is the characteristic equation. Now what we want? What is e raised to power? So 1 plus a, and this with the help of Euler's equation we can say cos phi minus j sin phi. G of s is known to us. What is that? B1s plus V naught upon A2s square plus A1s plus A naught, right, into GCS. GCS is Kp plus Ki upon S. So equal to 0, right? So this we get. Now in this equation, what we do put, we are doing, tuning this Kp and Ki using stability boundary locus method. So what we do, we put S equal to j omega here. We want to obtain everything in terms of frequency. So 1 plus this term. Now instead of this S, we are putting j omega plus b naught divided by S square. So this is j omega square. It is minus a2 omega square plus a1 j omega plus a naught. Kps, kp j omega plus ki s j omega equal to 0, right? Now we can cross multiply and rearrange them, right? So after rearranging, we rearrange them in such. So after rearranging, what we will find, there will be few terms which are constants. There are few terms which are in multiplication of j, right? So we rearrange them in such a way that we rearrange first all the terms of uh, real in nature together and all the terms of imaginary nature together, right? And within the terms which are real, we do in such a way that kp and then its factors, ki then its factors, then constant. Similarly, plus j, kp and factor of this plus ki and factor of this plus constant term equal to 0. Now this equation, this equation is function of here various terms kp, ki are unknown to us. Re1, Re2, Re3, Im1, Im2, Im3, they are having value as follows. Re1 is equal to a into minus omega square p1 cos phi plus omega v naught sin phi. Like that we will have. So far here simply we have used mathematics to simplify these equations, right? So here now what we can do, we can separate these terms. So this is just 0 plus j0, so we can separate these terms. So this is kp real 1 plus ki real 2, that is equal to minus real 3. Similarly, the second term to be 0, kp im1 ki im2 equal to minus im3. So these things are there. Now these two equations we get. Now what we can do, we can simplify these two equations in terms of kp and ki, right? We can simplify these terms in terms of kp and ki. So this becomes function of re1, re2, re3, right? And also im1, im2, im3, similarly ki. So we can solve this for kp equal to something, ki equal to something, right? So next is like that only. We have solved this for kp and ki and then put in re1, re2, re3, im1, im2, im3, we have put these values, right? So after again rearranging, we get some terms like that, where Q3 is minus A2B1, Q2 is minus A2B naught plus A1B1, Q1 is minus A1B naught plus A naught B1, Q naught is A naught B naught, P2 is B1 square, P naught is equal to B naught square. So this all A1, B1, A naught and your A1, A2, A naught, they are known to us, right? They are known to us. And sorry, B2 is not there. So V node and V node 1, then A node, A1, A2. They are known to us. They are just the coefficients of the converter transfer function. So all these terms are known to us. Only unknown here is phi, omega, and A. phi, omega, and A. So we have two equations. We want to find Kp and Ki. So you might have seen that in the gain phase tester, we have considered this to be gain phase tester, right? So when we have phase margin to 0, we put phi to be 0. It means phase margin is 0. So this is corresponding to minus 180-degree crossing. So whatever is the gain there, that is A. And when we put A equal to 1, that is the crossing of uh, 0 dB line. So at that point, phase will be phi. So we will take two conditions to calculate the value of kpki corresponding to phase margin A. We will put phi to be 0. To calculate the value of kpki corresponding to phi, we will put A equal to 0. Right. So we will put A equal to 0 and phi equal to 0. So equations will be simplified. But because normally in converters, as we have seen, this condition that gain margin is always infinite, right? So we will not, if it is already infinite, then we will not set A. Why we will decrease this? So for this we will not go. We will just go for A1 equal to 1 and phi, right? But anyhow, if we put this, then we can get two locus, and omega definitely we will vary, right? Omega we will vary. So now by varying omega, we can obtain two boundary locus in KPKI plane. So first is for specified value of phase margin phi, which will be obtained by setting A equal to 1, as I told. Second, for a specified value of gain margin A, which will be obtained by setting phi equal to 0. The intersection of these two boundary locuses, so let's say, for example, let us say this is the one boundary locus. This is Kp, Ki. We are plotting this boundary locus, and another one is something like this. So this one is, let's say, for phase margin 60-degree, right? And let's say this is some gain margin 2, for example. Now, what does this approach says, right? It approach says that if you take any value of kpki boundary, within this boundary, then it will guarantee that your phase margin, your gain margin will be at least 2. Similarly, if you take any value of kpki within this plot, then your phase margin will be guaranteed 5, that is, let's say 60-degree. It means if I want to meet both the condition together, A equal to 2 and phi equal to 60, then what I need to do, I had to take the common part of that, right? So common part of that, it means, let's say this one. So I had to take common part of this. It means if this one, right? Common part of both, intersection of both. So if you choose kpki within this, then what will happen? Then your phase margin and gain margin both will be guaranteed. Phase margin of 60-degree and gain margin of 2 both will be guaranteed, right? But in converter case, if phase margin is already, gain margin is already very high or infinite, then we have just one single locus, and within that we need to choose the Kp and Ki. So for DC to DC converter applications, normally gain margin is infinite. Therefore, only one boundary locus is sufficient to ensure the desired phase margin, right? So let us see one practical case study over here. So this is buck converter. We are using PI controller. We are designing PI controller for the buck converter using the stability boundary locus. So we have chosen a range of, any doubt here, please ask. If you have any doubt so far, before we discuss the results and application. no doubt. It's a very interesting algorithm. If you work on converters for any applications in microgrid and vehicles, so primary control, you may use this. Very nicely we can tune. Okay, so if no doubt, then we go ahead. Okay, so here we have taken the input voltage variation 16 to 24, and the nominal value is 20 volt. Nominal value is 20 volt. So we have taken -4 variation here and +4 variation. So 16 to 24 volt variation we have taken. Now output voltage regulation we have decided to be 12 volt. Yes. If input varies, then also our output voltage should be 12 volt, right? Now load variation, we can do 11 ohm to 22 ohm, right? And inductance value we have taken 1.1 millihenry with its parasitics. Capacitance 84 microfarad, 0.3 ohm. So you can say why 84 microfarad? Basically it was printed 100 microfarad, but printing is something different and actually is something different. So we measured when we used, so it was 84 microfarad only. So that way it was, we have taken this value as it was in hardware at 84. If it could have been 87, we could have taken 87. If it could have been something 92, we could have taken 92. But printed one was the 100 microfarad. Well, so the switch we have used IRFN 540 MOSFET. So whose resistance is this, or maybe if I'm forgetting, then this is Z44, either of these two. So diode forward voltage diode in hardware we normally use MUR or MBR 860, 460, 1560. That depends upon your current rating. So any of these diodes we use. So these diodes are not the normal diodes. These are fast recovery diodes, Schottky diodes, which we do use in converters. We do not use conventional like 4708, that kind of diodes which we use in rectifiers, diode bridge rectifiers, that we do not use in DC to DC converters, right? Okay, so switching frequency was 20 kilohertz, and as we kept sawtooth waveform to be 1. So for this, we want to design a controller such that despite these variations in loads and the inputs, our output voltage should be regulated. That is our target, right? So by putting these values, we have already derived the formula. By putting these values, we get this transfer function. Okay, we get these transfer functions, and now this transfer function we plot body diagram. So this body diagram shows that here this is having steady state gain or DC gain is constant. So if you do the control analysis of the systems, then for step variation in the input, steady state error will be constant. It will not be 0, right? And similarly, the phase margin is positive, gain margin is infinite, but phase margin is 26° only, right? So phase margin is not good enough. So we need to improve the phase margin. That is the target. So VSW we have taken 1, so VSW is 1. So our transfer function, loop transfer function or uncompensated transfer function becomes this one. So you can see here also that this is our 1 here. 1, right? This is our 1. So it is not reaching to steady state without controller. For uncompensated system, it is not reaching to steady state. So this transfer function is done. Now this transfer function, for this transfer function, I need to design a controller. Let us say I am designing PI controller as discussed, right? So if I can compare with the standard transfer function, then B1 is this, B node is this, A2 is this, A1 is this, A node is this. That is there. Now substituting these coefficients in 5 and 6, we get Kp value, Ki value. right? We can get KP value and KI value. So and what is our not mentioned here? Yes, yes. So okay, KP and KI value we mentioned. Then it is the KP equation and this is KI equation. Now, as I said, A I will keep 1 because I am tuning this for phase margin only, and my target phase margin is 75 degree. My target phase margin is 75 degree. So for this 75 degree phase margin, we are going to tune the PI controller. So what I will do, I will put this phi equal to 75 degree here. So this cos phi sin phi also being calculated and merged into this constant only. So what is left only? So now phi is also gone. So this Kp is function of omega and Ki is also function of omega. Kp and Ki both are function of omega, right? So now I take one value of omega. I can write a MATLAB program, right, in which I put these two expressions. I substitute some value of omega, then I will get Kp and Ki, another value of omega, another value of omega. Like that, I will have thousands of points Kp and Ki. So I'll plot them. So when I plot them, then let's say this is some value of omega, this is some value of omega, this is some value of omega. Like that, I have obtained one locus, right? Like that, I have obtained one locus. Now, this locus, this one, this gives me the region, stability region, 4 phase margin greater than 75 degree, greater than 75 degree. So you'll be able to see here there are values which are like Kp values. If you see, Ki values are positive, but Kp values are negative also. So normally negative values we discard, right? Mathematically it is okay. They will provide the 75 degree phase margin, but when you are going to implement, then you cannot implement this PI controller in experimental work. So our actual the possibility of KPKI becomes right to this y-axis, right? So I have chosen, okay, so just so I have chosen, I can choose any value, positive value of KPKI combination, which will give me 75 degree phase margin. So I have chosen this value, right? This value. So corresponding to this value, Kp is 0.02 and your Ki is 20. So my transfer function becomes Kp Gs becomes 0.02 Kp plus Ki upon S. So that is 0.02 S plus 20 upon S. So this is our transfer function for PI controller. Yeah, this one, right? Now what I can do, I can again, I am already having GS. Now I have obtained GCS. So both I can multiply, right? And then again for combined, this is called compensated system. Compensated system. So for this compensated system, what I can do, I can plot the body diagram, body plot, right? So this is uncompensated system, blue one. Then this red one is the green one is the PI controller, and this red one is the compensated system. So let us analyze this red one, compensated system. So what you can observe here that earlier our gain crossover frequency was here, and our this margin was like this only, small one, 26 degree, right? Now due to this PI controller, my crossover frequency has shifted to left, right? Crossover frequency has shifted to left. That's why now my margin has increased to this one, and it has becomes 10 degrees, 107 degree, 107 degree, right? Now margin has improved, but crossover frequency has shifted, right? Due to which, as I told, like this phase margin is related to overshoot, overshoot, and this crossover frequency is related to settling time. Frequency, that's why settling time, right? So these two parameters are important, but crossover frequency has reduced here. Why it is reduced? Because this PI controller gives only the uh, PI controller provides only the negative phase. So we will see in afternoon class PI lead how to cover this, right? So now crossover frequency has reduced, but phase margin has improved. And also what you can see here, that this DC gain, right, low frequency gain, is also having mine earlier blue one. So it was constant, this was constant, but this red one, now this red one is having minus 20 dB per decade slope, minus 20 dB per decade slope. And this minus 20 dB per decade slope is there. That's why now steady state error will be zero, which we can see in these step response also. So earlier we were having this red one response, right? So this red response was having steady state error here and large overshoot, right? But because we have tuned PI controller, so that our overshoot has decreased, right? This is below 1 only, overshoot has decreased, right? Not has decreased, it has been eliminated, but because overshoot has been 107, so now this uh, but steady state error, you can see steady state error has been removed. So three impact we can see. First, impact of minus 20 dB per decade, steady state error has removed. Second, improving phase margin, so your this overshoot has gone down. Third impact, that is crossover frequency has reduced. So this is adverse impact. This is not what we desired. Due to which, what was happening earlier, it was reaching to steady state earlier only, but now it is taking time to reach steady state, right? So that is the one adverse effect, too important, right? So we can improve even this settling time by so it means its transient response has been compromised. So that we can do, we can improve, and that we will see in another techniques, which is PI lead controller, PI lead controller, in which this particular response has also been will be increased, right? So it's results. So if you see results, then this is the buck converter. So this is input variation. Let me see. Sorry, it's coming. Anupam, let me know once sir joins. I will stop my session.
Okay, sir.
हाँ, बता देना. I will stop my session.
Sure.
Okay, so these are the results. Buck converter PI controllers. So I wanted to design this controller for mitigating input voltage variations. So my input is 16 volt and output is 12 volt. Now input has been increased to 24 volts suddenly, but because I have designed the controller, so as voltage has increased, the output is also increased. But because I have designed a controller, so output is again settled to desired voltage 12 volt, right? But yeah, it has certain overshoot and it will take certain time, right? So the R is kept at 11 ohm. Now R is kept at half load 22, and again this is variation from 16 to 20. So we can see that this variation is being tracked, right? Similar to previous one, and in experimental also this is tracked. Now the next case is that we have kept input voltage to minimum, input voltage is fixed, and now load is changed. So if load is changed, then what we can see, that output voltage is also regulated. In next case, the input voltage is kept to the maximum value and the load is also varying. but output voltage is remaining constant. Output voltage is remaining constant, right? The next case is that if I am changing my reference voltage from 12 to 15 volt, then my output voltage is also being tracked from 12 to 15 volt, and this we can see in hardware results as well, right? Now what we are seeing that even if there is variation in load current, input voltage, load current, reference voltage, output voltage is being tracked. So that is what we wanted. But the issue here, or the further scope for research here, is that the the overshoots it is taking, the overshoot it is having, the time it is taking to settle down, right? So these things can be further improved, right? And that's what we go for another controllers, right? So with this I complete my presentation here, and we will go for another control technique in the evening lecture. So thank you very much. If you have any doubt, please let me know. I'll be happy to answer. Where gain margin and phase margin will be given. Yes, whether gain margin. Yes, ma'am. So that is our design only. As a designer, we need to decide what gain margin and phase margin I should set so that I can meet the given performance. Right. So let's say we are given this much overshoot is allowed, this much certain time is allowed. So based upon that, we need to, or it is better if the user gives us in terms of frequency domain, but user does not know what is frequency domain. So they will give, I can allow this much overshoot only. I need, if there is any variation, my output voltage should settle in this much time. So those time domain specifications we can translate into, there is formulas for that, we can translate into frequency domain specifications, and based upon that we can tune our uh, based upon that, yeah, we can use this kpki formula and get our stability boundary locus and tune the pi, kp and ki. So that we need to fix what phase margin we need to have. I hope I partially answered your query. Any other doubt, please? Okay, so we stop here. We will wait for 2 minutes, and next speaker will be there. Thank you. अनुपम, अनुपम, हाँ अनुपम।
यस सर।
सर को एक्चुअली क्या, वो पेनलिस्ट में नहीं जा पा रहे हैं, इसमें है ना, इसमें है, अटेंडीज में है। तो आप सर
ओके।
को अनम्यूट करके वो बनाओ ना होस्ट में, इससे
हाँ सर, एक सेकेंड।
ताकि शेयर भी कर पाए। अभी सर डिस्कनेक्ट हो गए क्या वापस? अभी तो दिख रहे
सर
थे।
शायद डिस्कनेक्ट हो गया सर, अभी है नहीं।
वापस ज्वाइन करने को बोलता हूँ मैं। अभी जैसे दिखे ना, तो
हम्म।
सर अभी अटेंडीज में भी नहीं दिखाई दे रहा है।
नहीं सर।
हाँ, वो पासवर्ड सही से डालेंगे हो जाएगा। अनुपम आप बनाओ अनम्यूट करके पैनलिस्ट, अभी सर अटेंडीज में तो है ऐड।
हम्म,
अभी फिर अच्छा, फिर से वो सर ने फिर से लॉग आउट करके शायद वो दूसरा वाला ही करना चाह रहे हैं। सर नॉर्मल वाला ही कर लीजिए, फिर उसमें बना देते हैं जो पहले कर पा रहे थे। नॉर्मल वाला कर लो, उसमें अनम्यूट कर देंगे, उसमें पहले जो हो पा रहा था ना उसी में कर दीजिए। पहले जो कर पा रहे थे ना आप वही कर लो, फिर ये नहीं हो रहा है तो।
पहले मीन्स।
पहले अटेंडीज में किया था सर ने।
नहीं
वो
सर, अभी तो नहीं दिख रहे मुझे
आप नहीं है,
अटेंडेंट।
वो लॉग आउट करके फिर से मैंने उनको बोला तो वो उसमें जा रहे हैं। पर अब देखते हैं, जिसमें आएंगे उस उधर से अनम्यूट कर देना। हो गई क्या ज्वाइन? नहीं, ईमेल आईडी तो ऐड ही होगी यार, वो तो पहले से ही दे रखी है हमने, पिछली बार भी तो किए थे ना सर। नाम ही नहीं कर रहा आप सर। अच्छा अच्छा अच्छा। हो जाएगा तुरंत। अच्छा, पिछली बार कैसे करवाया था? पिछली बार कैसे करवाया था? अटेंड ही हुआ है। तो अभी भी अटेंड ही बोल देता हूँ ना। चलो मैं दो दो नहीं कर रहा हूँ, भेज रहा हूँ आपको व्हाट्सएप। भेजा मैंने आपको व्हाट्सएप पे। हाँ sir, yeah, now you are visible and audible both. Yeah,
Yeah.
welcome.
Thank you. Thank you. Sorry for.
No, that's okay. So we welcome Professor Ujjwal Kumar Kalla sir from NIT Delhi. He has already taken one session, so he will continue his discussions. So welcome, sir. Over to you now.
Thank you. Thank you. See, is my screen is visible now?
Yes, sir.
Okay. So today we will discuss about the implementation of analog control scheme for multi-pulse battery charging systems. Okay. So battery charging means basically battery charging is AC to DC converter system. Basically, battery charging is a AC to DC conversion system that converts AC to DC and then supply the regulated DC power to the battery. Okay. Now, what is the requirement of the battery? Battery requires DC power for its charging, but commercially we have only AC power. Okay. So, in 99.99% cases, we need to convert that AC power into DC power first. Okay. Then we have to make the voltage level and current of the DC power of such value that it should meet the charging requirement of the battery. Every battery has maximum charging and discharging current rating. Every battery. Okay. And every battery has maximum charging voltage also. So first requirement for the battery charging is the first requirement for the battery charging is we should know the voltage rating of the battery. At first we should know about the voltage rating of the battery. Okay. Then maximum voltage, allowable voltage, charging voltage of the battery. Suppose if you have a 12-volt battery, so charging voltage should not exceed to the 13.5 volt usually. Okay. In some cases maybe 14 volt, maybe 14.5 volt, But usually 12 volt battery should not be charged beyond 13.5 volt because it may be damaged. So what is the maximum charging allowable charging voltage? That is always mentioned on the specification of the battery itself. Okay, that is the major specification of the primary specification or major specification of the battery for any battery. Okay, so it doesn't matter whether it is lead acid battery or nickel cadmium, whatever the type of battery, there will be one charging voltage and there will be one maximum allowable charging voltage. So at any cost, we should not apply the charging voltage to the battery beyond the maximum allowable charging voltage. One thing. Second thing is maximum allowable charging current. Every battery has its own allowable maximum charging current that is always mentioned on the battery itself only. That is the primary requirement, primary specification of the battery. Okay, so before charging any battery, you are supposed to know these four parameters initially. Okay, and essentially first is the battery, usual battery charging current, maximum battery charging current, then charging voltage and maximum allowable charging voltage. So what are the major limits? Maximum allowable charging voltage and maximum allowable charging current. Okay. Now see, so how the battery is charged. So internal resistance of the battery plays an important role while we design any charger for the battery. Okay. Usually the internal resistance of the battery is very less. So if the internal resistance of the battery is large, high, in that case, the heat generated during the charging will be very high. So battery will get heat up during the charging if the battery has higher internal resistances. Okay. So in case of higher internal resistances, the battery heat will increase during the charging and discharging both. Not only during the charging, during discharging, again because same current will flow through the internal resistance. So I square R loss will be there in the internal resistance of the battery. So because of that I square R loss, the battery will get heat up during the charging as well as during discharging of that battery. Now, suppose I am taking a case of 12 volt battery. If you are using 48 volt battery, okay. So in case of 48 volt battery, you can apply the uh, 13.5 volt by 4. Okay. So it will be almost 13.5, 52 and 2. 54 volt. Okay. So 48 volt battery bank should not be charged beyond 54 or 55 volt usually. Okay. In some cases, overcharging is requirement of the system because of meeting some emergency requirements. Okay. So usually the 12 volt batteries should not be charged beyond 13.5 volt practically. Now next is the charging current. Life of the battery will reduce significantly if the charging current of the battery will exceed to the allowable limit in any case, and that will firstly degrade the status of your battery, the material of the battery, charging and discharging process of the battery if the charging current rating increases beyond the allowable limit. So in any case, the battery charging current should not exceed to the allowable charging current. So how much will be the charging current? How much battery will take the charging current? That depends on the internal resistance of the battery. One thing. Second thing, voltage applied across the terminal of the battery during charging. Okay. And the potential difference voltage difference between the battery terminal voltage and charger voltage. Okay. So when we divide the difference between the voltage, terminal voltage minus battery charging voltage by internal resistance, we will get the charging current. So if terminal, there the difference is high, because internal resistance will remain constant for the given battery. For any given battery, the internal resistance remains almost constant, but charging current will increase whenever the charger voltage will increase. Okay. And the difference between the charger voltage and terminal voltage will increase, not only the charger voltage. Okay. If your battery is deep discharge, suppose if your battery is 12 volt battery discharge up to 10 volt. Okay. So there will be a difference of 2 volt. Okay. And if your internal resistance is suppose 0.1 ohm, then 20 ampere charging current will flow. But if it is 0.01, then 200 ampere charging current will. So the difference voltage, 2 voltage divided by 0.1. That 0.1 is the internal resistance. If the voltage difference is divided by the internal resistance, you will get the charging current. Okay. So how we maintain the charging current during the charging? What we do? We increase the charger voltage gradually. As the terminal voltage of the battery increases, we increase the charging voltage in order to maintain the constant charging current. So that is the basic theory of the battery. See, that is like that. So initially battery will operate in constant charging current. Initially battery is usually charged in constant current charging mode, and once it reaches to close to the terminal voltage, means battery voltage, suppose 12 volt battery is has been charged already up to 12 volt almost, then we shift that constant current charging into the constant voltage charging. Then we shift that into the constant voltage charging. Okay. As this graph shows. Okay. So when we shift the mode of operation from constant current to constant charging voltage, then what happens? The charging current decreases. In constant voltage charging mode of operation, the charging current decreases. Okay. In constant current charging mode of operation, okay, during constant current charging mode of operation, the charging current will remain constant, and this mode of operation is used during the starting phase till the battery terminal voltage reaches to almost its rated value. Suppose if it is 12 volt battery, then when battery terminal voltage reaches to almost 11.9 volt or 11.8 volt, we shift the mode of charge of the battery from constant current charging to constant voltage charging, because of beyond that uh, level we may not maintain the constant current charging. Okay, otherwise battery will be damaged. So we shift the mode of operation from constant current charging to constant voltage charging. Okay. So now there are several methods for the battery charging, but fundamentally two methods for the battery charging. In first method, what we do, we use multi-pulse battery charging system. We use multi-pulse battery charging system. Multi-pulse battery charging system means simply we are supplying AC power to a control rectifier, and output of the control rectifier is supplied to the battery. Okay. So by controlling the delay angle of this control rectifier, single phase control rectifier, we can control the terminal voltage of the battery and the charging current of the battery. Okay. So that is called 2 pulse, 6 pulse, 12 pulse, 18 pulse, 24 pulse. These are the multi-pulse charging systems. Okay. Another method is the VSC based, voltage source converter based charging method. Okay, in that case, we may use bidirectional charging systems also. So for that we may also use VSC, voltage source converter, for the charging, and we will connect the battery at the DC bus of that VSI. Okay, and between that VSI we may also, and battery, we may also use bidirectional charging system. Okay, so here in this case, in this lecture we'll discuss only the multi-pulse battery charging systems, that is 2 pulse, 6 pulse and 12 pulse battery charging system, and how we implement the analog control in these schemes. Okay, am I audible to all of you?
Yes, sir.
Am I audible?
Yes, sir. Fine.
Okay. So, so this is 2 pulse battery charging system. Okay. These multi-pulse battery charging systems are made of thyristors. Okay. The major advantage with the multi-pulse battery charging system is the robustness. Multi-pulse battery charging systems are made of thyristors, which are highly robust among all power electronics switches. Okay, I am working since last 15 years in this area in laboratories. I find that thyristors are very robust. MOSFETs are very sensitive devices. Okay, if your voltage rating, current rating, or any spike will exceed to limit, even for a microsecond, it will burn. But thyristor is a very rugged device, as well as the inductive coil. Okay, that is never damaged with the small spikes. They are very well, they are very good technology as far as robustness is concerned. So this is single phase 2 pulse battery charging system, where we are using 4 thyristors. Okay, and we are controlling the charging parameter by controlling the delay angle of this 12 2 pulse charging system. Okay, so we control the delay angle in such a way that the charging current should be maintained constant. Okay, we do not bother about the output voltage of this converter. Okay, initially, once the battery voltage reaches to close to its rated value, then only we bother the output voltage. Okay, so initially we increase the voltage. Okay, okay, we keep very less voltage, which is slightly greater than the battery voltage. If battery voltage, suppose battery is discharged, 12-volt battery has been discharged to 8 volt, then we will keep the charging voltage 8.1 volt only. Okay, so because of only 0.1 volt, suppose 10 ampere battery charging current is going to battery. Okay, so now battery will be also charged to 8.1 volt. Then we'll increase the output voltage to 8.2 volt. Okay, then again battery will also charge up to 8.2 volt. Then we will increase the output voltage to 8.3 volt. Then again battery will also charge up to 8.3 volt. Then we will increase to 8.4 volt. Battery will also charge to 8.4 volt. So gradually we increase the output voltage of this 2 pulse converter, so that the charging current is maintained. So now what is the issue here? Because of this 12 pulse charging system, there will be second harmonic present in the output current, okay, of 100 hertz. Okay, so see, when battery will be charged, almost charged, the power quality of the source side current will be very poor. Okay, and the magnitude of the TSD may reach to 80%, 90%. Okay, and power factor may be poor than 0.2. Okay, or 0.3. So in single pulse 2 pulse battery charging system, there is a very serious power quality concern. Because of these power quality concern, the power factor becomes very low, maybe poor than 0.2 or 0.3. Okay, so these are the simulated waveforms. See the second waveform, that is the source current, you can see that is highly non-sinusoidal. Okay, and battery voltage and battery current, third and fourth waveforms, these are also having ripples, okay, are having second harmonics. Okay, and see here the THD is almost 91.48%. So this THD will vary depending on the charging current. So as the charging current will reduce, the THD will increase. So if charging current is high, then THD will be less. So the THD of this two pulse converter system will vary from 20% to 90% or 100%. Even in some cases, it may be 140%. Okay, that I observed. Okay. And these are the source voltage and uh, uh, see, the source is the grid voltage. So grid voltage THD is very less. Okay, but grid current is very high. THD will become very high because of this two pulse converter. Now we come to the six pulse converter here. Okay, so in this six pulse converter, we are having three legs. In each leg is having two thyristors. So total six thyristors are there. Again, we have developed one embedded MATLAB function block. Okay, for the digital control of these thyristors. Okay, so by controlling the operation of this thyristor, again we are increasing slightly the terminal voltage in order to maintain a constant charging current of the battery. Okay, so here we are taking the battery voltage as a feedback variable, and we are comparing that battery voltage with a constant charging current. Okay, so we'll get a current signal that we will process through the PI controller. Okay, so sorry, we are not we should take voltage and current both. If we are maintaining, if we are using constant voltage and constant current method, if we are using only constant voltage battery charging method, then you should use only sense only battery voltage. And if you are using only constant current battery charging scheme, you need to sense the current. Okay, and then process that error through the PI controller and send the output to the current limiting unit. So current limiting unit decides that in any case the output current should not exceed to the maximum allowable battery charging current. Okay, and these are the performance, power quality performance of the 6 pulse battery charging system. See, the again the charging current is highly distorted. Okay, but it is better than the 2 pulse converter. Okay, so in this case usually the THD does not increases beyond 35 or 40%. In two pulse system, it may reach up to 80%, 100%, or 140%. But in three phase system, usually in six pulse system, usually the THD of the source current remains within the limit, uh, less than 40% almost. Okay, and this now this is 12 pulse battery charging system. In this 12 pulse battery charging system, we use two breezes, okay, of 6 pulse. Both are connected in series, and we are using transformer here. The delta primary is delta connected, secondary one is a star connected, another one is a delta connected. Okay, so one 6 pulse converter is connected in the output of the star connected winding, and another pair of 6 pulse converter is connected in output of the delta connected winding, and the output of both of these two converters are connected in series. Okay, so that output will become 12 pulse. Okay, so in this 12 pulse converter system, the power quality of the source current will be significantly improved in comparison to 2 pulse or 6 pulse system. So you can see here the source current is almost sinusoidal. It is looking almost sinusoidal. Okay, and output voltage and output current are also having very less ripple in comparison to 2 pulse and 6 pulse bed charging systems. Okay, here see the SOC, state of charge, is increasing, means battery is in the charging mode. Okay, so here see the THD is less than 15%. Okay, So if we manage the inductance of the transformer, okay, in such a way that it will filter out the major harmonics of the current content, in that case this THD may be less than 5% even, okay. And then we have developed this analog controller, okay, for this control. This analog control is the generalized controller that we have developed, and this generalized controller means same controller. By increasing the number of controller, we can use for 2 pulse, 6 pulse, and 12 pulse, okay. So this is the structure of this converter here. So this generalized controller is made of constant voltage and constant current mode of operation, okay. It's having its dual DC power supply. Dual DC power supply means it is giving a regulated plus minus 15 volt supply for this control card itself only, okay. And see, here we are using this for the 6 pulse converter, okay. So here we need 3 sensing transformer for 6 pulse, and for 12 pulse converter we required 6 sensing transformer. One sensing transformer is required for the 2 pulse. So for 12 pulse we require 6 sensing transformer and 6 cards, okay. So 6 card, each card will be for 2 pulse, okay. So this is the scheme for 12 pulse charging, where this is a primary winding star connected, and secondary is one is star connected and one is a delta connected, okay. So star connected also has 3 phase 6 pulse thyristoride base in its output, and delta connected secondary winding also has one thyristoride 6 pulse bridge in its output, and both the thyristor bridges 6 pulse bridges are connected in series to make this system 12 pulse, okay. So all the triple N harmonics will also be eliminated in the delta winding, okay. And now the 6 cards will be used for this analog control, okay. So 6 sensing transformers are used here, okay. And this is the photograph of 2 pulse battery charging system, okay. And this is see, these are the generalized electronic controller, okay. For 6 pulse system we have used 3 cards here, okay. Okay, and this is current sensor, okay. And these are thyristors, okay. And this is inductor filter, and this is capacitor filter, the output. And see, this is a photograph of 6 pulse system, and this is 12 pulse system, okay, that we have 12, okay. In 12 pulse, see, the thyristor bridges are connected in series like this, and that is the transformer for 12 pulse that we have 12, okay. And this is the switch arrangement for 12 pulse scheme. See, in experimental results also, THD is very high for single pulse and 3 pulse, whereas THD is comparatively very less in case of 12 pulse systems. So that is all about the 12 pulse charging system, okay. And my screen is visible. Am I audible?
Yes, sir, fine. Screen also visible.
Okay. So see, that is the implementation of improved power quality 12 pulse charging system, where we are using these 2 6 pulse bridges in series, okay. So there are almost 10 topology also available through which we can use 12 pulse, we can implement the 12 pulse charging system, okay. And a lot of work has been reported in the literature, okay, throughout the world in last 30 years on these multiple charging systems, because these charging systems are very robust. That is why still in 80% UPS in India this scheme is being used. Okay, railway is also using this 12 pulse battery charging system. Indian Railway. Okay, I am having one industry project. In that I am developing this 12 pulse battery charging system for a company. Okay, so these are still in use in India, in so many countries, because of these are so robust, so they require very less maintenance. Okay, so in this scheme we use 6 sensing transformers. Okay, and these sensing transformers are providing the information about the starting point of the voltage and current. Okay, for the control cards. Okay, so that control card can decide the delay angle. So these sensing transformers are primarily used to sense the delay angle of these 6 phases. Okay, and then we also implemented this scheme in digital using this control algorithm. Okay, so this point was taken as a reference. Okay, for the calculation of delay angle in this digital control scheme. Okay, and this is 6 pulse charging system and 2 pulse. So this is also a generalized multi-pulse battery charging scheme in digital mode. Okay, and this is the analog control scheme in detail. Okay, and these are the internal signal of the converter. Okay, controller. Sorry. Okay, so that we have developed in 2017. Okay. So this is 2 pulse battery charging system. This is 6 pulse photograph of 6 pulse battery charging system that we have developed in the laboratory, and this is the photograph of the 12 pulse battery charging system, where we are using 6 sensing transformers and 6 generalized control analog control cards for this 12 pulse. And this is one of the 6 pulse thyristor base, the another 3 pulse 6 pulse thyristorized base, and both are connected in series to this bus bar, and these are connected in the output of this transformer. This is 12 pulse transformer having 2 winding in secondary, one star connected, one delta connected. One star connected is connected to this converter set, and another delta connected winding is connected to this another converter set. Okay, so that is the hardware. So see, in this slide you can see the current of, see, this is the current of single phase. Third one is the current waveform of 2 pulse charging system, second is the for 6 pulse charging system, and third is 12 pulse charging system. So here, by managing the LC filter, see the THD of the 12 pulse charging filter system comes less than 5%, that is 4.8%. Okay, so this scheme is really highly recommended. Okay, so that is all about the 12 pulse battery charging system. So we may also implement 18 pulse and 24 pulse schemes. So now session is open for the query. You may ask any query. Any participant can ask any question related to multiple battery charging system, any kind of battery charging system you can ask for. If even if you have any other laboratory problem in the area of power electronics, you can ask me.
Sir, sir, can you please explain the concept of constant charging and constant current charging, constant voltage charging?
Pardon?
Can you please explain the concept of constant voltage charging and constant current charging?
Yeah. So there are 3 basic mode of charging method: constant voltage charging, constant current charging, and combination of constant voltage, constant current charging. Okay, means combination means, in combination constant current will come first, constant charging, constant voltage mode of operation. Okay, so first is the constant voltage charging methods. In constant voltage charging method, just we apply a constant voltage across the battery charging, or that is very dangerous for any battery. Okay, so but the cost of this charging system is very less. What we do, just we use one rectifier, we convert that AC into DC, and we apply the 12 volts across the battery terminal. If the battery is 12 volt battery, just we apply the 12.5 volt or 13 volt across the battery. Then what will happen, during the initial charging period, the difference between the terminal voltage of the battery and charger voltage will be very large. Suppose battery is discharged up to 8 volt and your charger voltage is 12 volt or 13 volt, say. So if charger voltage is 13 volt and battery discharge up to 8 volt, mean there will be 5 volt difference. Okay. So if uh, uh, the internal resistance is 0.01 ohm, then 500 ampere charging current will flow initially. Battery will charge very fast, okay, but it will reduce the life of the battery, life cycle. So every battery has fixed uh, charging and discharging life cycles. Usually lead acid battery has 1250 charging discharging cycles. Okay. So if the charging current does not exceed to the allowable maximum current value, if the charging current will exceed the allowable maximum charging current, then the battery will charge up to 1000 or 800 times only. Okay. So the charging discharge, maximum allowable charging discharging cycles of the battery will reduce from 1250 to 800 or 700, 500 or 600 if we will use the constant voltage charging. Another method is constant current charging. Okay. That is a better method than the constant voltage charging, but initially it is good, but when it reaches to the battery charge up to the almost to the rated value, in that case this control scheme creates problem. Okay, because of that time it that is becomes very difficult for the converter to pump the current when the battery is almost charged. Okay, so in that case, so complete charging system is the constant current and constant voltage. So initially the battery should be charged in constant voltage mode of operation, and sorry, constant current mode of operation. When the battery voltage reaches close to its terminal value, suppose it's a 12 volt battery and battery voltage has been reached to 11.5 or 11.8 volt, then this mode of operation should be switched from constant current to constant voltage mode of operation. Are you satisfied?
Yes, sir.
I got it.
Yes, sir. Fine. And sir, how can we make an such algorithm that checks the battery voltage or charger voltage at this 11.5 or 11.8? Then we should switch.
Actually, yeah. What we do, we make the arrangement in the control algorithm that senses the, actually that is we vary the delay angle in order to maintain a constant charging current initially. Okay, but we check the put in this in the control that this mode should be applicable only till the battery voltage reaches to this value. Once the battery, there is a comparator. Okay, so that comparator always check and compare the battery voltage. Once the battery voltage reaches to its threshold value, immediately it removes the control signal of that loop and make that loop in active. Okay, and it starts another control loop that only supply a constant voltage to the battery.
Okay,
So,
fine.
so there are two control loops, one for constant current, one of constant voltage. So, and there is one logic block is there. So that logic block decides which loop will operate.
Okay. Fine, sir. Thank you.
Any other query? Any other query?
Any other queries, please? Sir, so I was having one query. So this number of pulses we are increasing, it is complicating the circuit, but like quality is improving. So it depends upon how costly we can bear the charger, right?
Yeah. Actually, it improves the power factor. It will reduce the reactive power demanded, and it will reduce the total harmonic distortion the source side current.
Yes,
So the power quality will be definitely improved in order to meet the IEEE 519 standards of the power quality.
so that's why we can go for like this much bulky, or we can say costly charger, right? In that term only.
Definitely, cost will increase, but it will improve the life of the battery and overall system.
Yes. So, sir, one more question, like let's say mobile battery or any battery, normally we say they have some fixed number of cycles, let's say 3,000, 5,000 cycles, charging cycles,
Yeah, yeah,
right? So
yeah.
many time in mobile or laptop, we charge sometimes 60%, then we take out the charger and then battery charges up to 20%, then we again charge, like randomly we do charge it. So how this charging cycle defines like,
No, no, then definitely the charging cycle will be reduced.
so every like even if we charge
Actually, that is,
10 minutes, then one cycle considered?
pardon?
If I say if let's say I charge for 10 minutes only, then also one cycle is covered like that.
No, not no, one cycle is covered, but the this is a very complex calculation. Okay, but there is a thumb rule. If battery is not charged properly, in that case, maximum allowable charging discharging cycles will be reduced every time.
Okay.
What, are you getting a point?
Yes.
So if you are using battery that is not fully charged, okay, so one charging cycle will be almost considered. Maybe zero point 0.8 you can consider, not one cycle. Okay, so the overall number of allowable charging discharging cycle will be reduced. Although it depends on so many parameters,
Yes. Yes.
not only on this, but finally it will reduce the life significantly. So
Yes.
battery should be
Yes.
fully charged.
Yes. So it's better we fully charge, then we disconnect the charger, then discharge it up to 10%, 20%, then again put charger. I
No,
think
no, no,
that will
not
be
10%. Usually, battery should not be discharged less than 70% or 80%.
make
If it will be deep discharge, then again the life of the battery will be reduced.
okay, 70%.
70% usually. It should not be discharged below 70 or 60%.
Okay.
In case of lead acid battery, 12-volt battery should not be discharged below the 10.5 volt.
Okay. Okay. Okay, sir. Thank you. Thank you so much. Any other query, please ask. I think there is no more queries. So thank you very much, sir, for delivering a wonderful talk on charging systems. So thank you very much.
Thank you. Thank you.
Okay, so we take a break of 5 minutes here and we'll wait for next presenter, next speaker. Thank you.
Thank you. Thank you.
Good evening, sir.
Good evening.
So let me give an introduction to you.
Please introduce Anupam.
Yes, sir. Dear participants, we have a new speaker, Professor Mukesh Kumar Pathak. Professor Mukesh Kumar Pathak is working in the Department of Electrical Engineering at IIT Roorkee. He joined IIT in 2007, and since then he is contributing extensively in teaching and research. He acquired PhD degree in electrical engineering from IIT Delhi in 2005 and has built a strong academic profile from over more than 2 decades. His research focuses on power electronics, electric drives, electric vehicles, solar PV systems, control of electric motors, and power converter for microgrids. He has published a substantial body of work with several hundred citations from research papers, reflecting his active research impact. He has also guided numerous postgraduate and doctoral students and delivered many expert trainings in power electronics and traction systems. He is also having experience on working on various projects worth rupees more than 4 crores. In addition to his technical work, Professor Pathak has held leadership roles, including serving as head of electrical engineering department at IIT Roorkee. He is recognized nationally as a leading academician in power electronics and related energy technologies. Now I request Professor Sir to please take over the session.
Hello. Okay, thank you very much, Dr. Manmohan, for giving me this lecture. So I'll share my screen and please let me know if it is about the slides. Can you see this screen?
Yes, sir. Yes, sir.
Okay. Okay, so I'm also trying to change slides.
Sir, it's working properly. Yes.
Now slide 1, 2, and so on, right?
Yes, sir. Yes, sir. Working perfectly. Thank you, sir.
Okay, thank you again. And I start with this. Should I start?
Yes, sir. Yes, sir. Please. Yes, sir.
So I will speak on solid state transformer for electric vehicle. In fact, very background of what solid state transformer is the first thing that we'll look at and also see what are its application other than EV. And we'll also talk about topologies, what are the demands or what are the requirements of different applications, and how these demands can be met by developing different types of solid state transformers. So as we know, the transformer is it is a very common part of the electrical power system or electrical system. In fact, we use transformer everywhere from generating stations, substation, and distribution. And there are, the power that comes to us may possibly be coming through many transformers. Sometimes it could be, uh, 10, 20, 30 transformers, and even more than that. And this power the transformer that we use in power system and in normal application is low frequency or line frequency transformer. This is a transformer which works only at 50 hertz fixed frequency because it takes 50 hertz supply and transforms it into different voltage levels and retains the same frequency, that is the input frequency. This transformer is a very simple equipment, set equipment in electrical engineering, and it's got very high efficiency, and it is relatively lower priced, less priced lower, and it has got high reliability. But this transformer, we have not we have been we are not looking at some of the disadvantages that this transformer has brought into the system, primarily in the present day scenario. The voltage, that output voltage, is more or less fixed. So you just cannot do anything more to regulate the voltage from the transformer except except that if you have uh, uh, automatic tap changing system, but that tap changing system is also has got a limited capability. So the voltage is more or less, we have to bear with the voltage, output voltage which comes. Sometimes this voltage becomes very high, some other times it will become very low. This transformer has got no capability of reactive power compensation, and it just supplies the power, whatever is the demand, both active and reactive power, it supplies through it, but it is not capable of mitigating the excessive reactive power demand of the system. And this demand is in turn transferred to the primary side or to the generating stations on the cumulative basis. As I said, it's a fixed frequency operation. So if you require operation of the system at some other frequency, you just cannot do anything. You have to have your own system to change the frequency. And above all this, we know that these transformers are suffering from a huge, size requirements and weight. They have got a very large amount of weight also. Sometimes this weight and size becomes, bottleneck in the areas, remote areas where the transportation is difficult. Even in the cities where the space requirement or space availability is very low, so you cannot place them. So this transformer has been serving the system for a long time and it's still there in the system. But what we foresee is now that solid state transformer will penetrate into the system slowly and slowly. And this penetration may not be directly in the form of transmission and distribution system, but it will come in the form of feeding some specialized loads. So this solid state transformer is capable of supplying, converting AC to AC. It can convert AC to DC. It can convert DC to DC. It can even convert DC to AC. So the transformer has got it is possible with this transformer to have any kind of input, whether AC or DC, and deliver any type of output, AC or DC. But since this transformer is having converters also, so many converters also, so efficiency is bound to be lower than the conventional transformer, where it is even more than 99%. And this transformer is capable of compensation, reactive power compensation, harmonic compensation. It is also capable of providing power or power flow in both directions. And the most important thing is that this transformer will have much smaller size as compared to the size of low frequency transformer or line frequency transformer. But all that, all the advantage that I said, they come at some extra cost, and there are disadvantages also. So the losses are increased, and that causes efficiency reduction. Cost is much higher. So typically with this transformer, you can reduce the size by about say 10 times or 20 times, 10 to 20 times. But that reduction in size comes at a cost, at a premium. And the cost is increased by 5 to 10 times, depending on what rating you are talking about. And since the system is highly complex, so complex control, and the chances of failure are also increased. But with these things in mind, we'll see how the solid state transformer can become capable or can become a future technology for many applications. So first, the architecture of medium voltage AC to low voltage AC solid state transformer. So the first of all, we'll see AC to AC conversion. That is the distribution level voltages, which is around 33 or 11 kV. How can it be converted to low voltage of 440 volt? There are many possibilities, and some of these all these possibilities are covered in these four type of systems. One is 3-stage SST. 3-stage means you have convert this AC, input AC, to high voltage DC, because this is high voltage AC, so this is high voltage DC. And then you have a solid state transformer or a high frequency transformer here, because solid state transformer is a complete system. So this is a high frequency transformer. That means just DC is converted to high frequency AC, and then it is passed through the high frequency transformer. You get high frequency AC output, which is again rectified to get low frequency, low voltage DC link. So transformation, because of transformation ratio, the voltage becomes lower. But the transformer link here is high frequency transformer link as compared to conventional system. Then the final step, where you want to get the AC out. So this DC is converted to AC by the output inverter. So you have an inverter here, a rectifier here, and transformer, high frequency transformer, along with a rectifier on this side and high frequency inverter on this side. So this is known as 3-state SST, because here you have one stage is high voltage DC link, the second is low voltage DC link, and third is the output stage. The second possibility is 2-stage SST with only high voltage DC link, no low voltage DC link, as we have seen here. So in this case, first the input is rectified to obtain high voltage DC, and this is then converted to high frequency AC, and using transformer you transform it to reduce the voltage and get the high frequency AC voltage, which is at a reduced tension. Then you convert it back to AC. So this low voltage DC link is no more there. So this becomes 2-stage. Similarly, the other possibilities are 2-stage system with low voltage DC link. So the transformer will come here, and this is the DC link, and then AC inverter here. And the last one is single stage, where there is neither high voltage DC link nor low voltage DC link. You have this AC is converted to high frequency AC, and this output or high frequency output of this transformer is converted to low frequency desired 50 Hz voltage. So there is no intermediate DC link in this case. Now, the other possibility is that we can develop this structure. Instead of having a single system, we can develop this structure of transformer, solid state transformer in a modular fashion. That is, this is one SST cell comprising of typical, uh, high frequency transformer, then conversion stage on the input and output sides. And then these SST cells are connected in a modular fashion. That is, you can connect them, all of them in series on the input side and parallel on the output side. So this becomes modular structure in which input is in series and output is in parallel. Similarly, another modular structure is input parallel and output parallel. So here both input side modules and output side modules are connected in parallel. The philosophy is that instead of having a single one transformer, very large transformer, why don't we use modular systems so that the reliability and efficiency are increased, because these modules, all of them may not function simultaneously, as is in this case. Depending upon the power requirement, you can bring in the module, you can keep it out. Similarly, the third possibility is input series and output series module structure. Now, another modularity that we can think of is like this. Here we can now, each phase we can have a number of modules. So this is one module, the second module, third, fourth, and fifth. So there is a 5 modules, and the MB stack, each of these phase will comprise of 5 MB modules, 5 for B phase, 5 for C phase. So in total, we will have 15 modules, and what these modules will do is, each one of them, input side, they are connected in series, and this the output side, these modules are connected in parallel to form the DC. So this is the neutral side, neutral of all of them. This one is neutral, and this is one phase, this is second phase, this is third phase. And the output of each module, each output is connected in parallel with this phase, and in parallel with these also, and in parallel with this also. Finally, all of them, all these modules together will form a large power DC link. So this is a low voltage DC link here, and we will have from this low voltage DC link, we can get the AC output by having individual DC to AC converters for each modules, or a modular DC to AC converters. So depending upon the power requirement, you can connect one, you can connect 2, or even more than 2 also, to get the supply the total demand. So this is the high frequency transformer. So instead of having one single transformer, we have 15 transformers here. And what we can do is we can operate these transformers at very high frequency, so that the size and weight of each one of them is much smaller than the total kVA rating. Suppose if this is 500 kVA, the total rating of this is also 500, but the size of these transformers would be much smaller than the 500 kVA transformer, individual transformer. This is another possibility. Now, this is also semi-modular ACC solid-state transformer, where the AC side is, input side is, the modules are connected in series, and then you have this high frequency transformer, and this is the final AC output, which is DC output, which is in parallel, and this is a single module, single output DC to AC modules. So this is a modular, as far as this is modular. You have modules here, many modules, but this on this side you have only one converter. So this becomes semi-modular system where the output is delivered by one module only. And you can see how will this work. You can have, the input side, you can have a rectifier, and then each one of these modules, you can have, this is one module, the second module, third module, and the output in parallel. This is another possibility. That means this, with this discussion will be now, what is emerging out is that there are number of numerous possibilities of developing solid state transformers. How you manage the topologies, what type of topology you have, how you connect them, whether you make them modular or you make them a single type of system. All that makes a lot of, brings a lot of possibilities. So you can see now in charging, this is medium voltage AC to low voltage DC. Now, what is a possibility? This is a charging system, suppose. What kind of charging system you can develop? The most conventional one would be you have three-phase supply, a conventional LFT, low frequency line frequency transformer. Then this is the 400 volt grid, and then you have AC to DC converter, and finally a charging or charger DC to DC converter. Here you can see the stages. This is a transformer stage with efficiency more than 99. This is a AC to DC stage. Typically, you can achieve efficiency of more than about 99. And similarly, this also you can achieve high efficiency, but because there are three stages, so overall efficiency would be about 97% or even less than that, depending upon the power, the loading conditions. This is the simplest system which is working, but you can change, you can improve it. What you can do is you can have a grid here, a filter, a low frequency transformer, and then AC to DC. Now instead of having AC grid, we have a DC grid here, and then you have DC-DC converters for each charging system. So this also will have better efficiency because you have individual charger. So the system here, this if you can see here, this charger will be a very large size, so it will supply many charging stations. But here it is individual one, so you can achieve higher efficiency. So slight improvement in as compared to this one. Then you can have the third kind of system, which has the grid, filter, and now there is a SST here. Till this point, till in the first, second type of system, we were not talking about SST. Now there was a low frequency transformer or line frequency transformer here. In this case, this is a solid state transformer. And what it is doing is, it is taking AC input and converting this to a DC. And you get a 400 volt DC link, and everything including this system, this whole system is now inside this solid state transformer. And finally, you have DC-DC converters for individual charging stations. So this is 1, 2, this like this. So this will have a slightly better efficiency as compared to this one, and comparable efficiency with this one. But what is more important here is that the size of transformer would be reduced as compared to these two situations. The third one is, the last one is, fourth one is, we have AC to DC and then DC to DC system. Now the solid state transformer here is doing every job, including what it was doing here plus this also. So that becomes a much lighter and much smaller system. So the target should be, now we should be moving towards this kind of system where this bulky or large size transformer is eliminated. So you can see how can we do this? This is a conventional system. You have AC converted to DC, then DC to high frequency AC, and then high frequency transformer, then the high frequency output, AC is converted to DC, and low voltage DC link, and then finally DC DC. And this modular structure will have LVDC. So what it will have is, this is MVAC, then this whole system is here, and then you have the output side, you have this converter. So in this case, all these functions all of them are subsumed in this one. This solid state transformer, if you compare it with the LFT, line frequency transformer, it is, even though this scheme appears to be good, but if you see the volume of the system is reduced in case of solid state transformer, but cost is not reduced, cost becomes higher, and losses also increase, and weight is also comparable, because now this is a contradiction of what I have been saying here, because solid state transformer here is coming with lot of power electronics converters. So volume and weight is contributed by power converters also, because the power converters are integral part of this solid state transformer. But if we are using this solid state transformer this is for AC to AC operation. If we are using it for AC to DC operation, fortunately, one stage or major stage is removed, and SST cost becomes comparable, losses are reduced, weight is reduced, and even volume is reduced by a large amount. So that is why right now we see an opportunity of SST finding its application in AC to DC operation, that is the charging systems. So what are the other application scenarios? EV charging is the one that I said. This is a EV charging system, conventional one, and this would be the SST-based EV charging systems. So the equipment here is transformer, then switchgear, then each charger. Here the system becomes smaller. So application scenario of SST, we have, this is low voltage AC to DC power supply solutions. Wherever we need AC to DC power supplies, we can use solid state transformers. We can, these are you can see here, DC to DC converter in the final leg, and before that we have a transformer, and this is a conventional solution, and this is solid state transformer solution, SST solution. So here the transformer comes first, then comes all the converter systems, whereas in this case transformer and converters are is a comprehensive solution, and these are the individual converters. You can use this for charging also. This solid state transformer can also be used for solar PV systems. You can see solar PV system has typically they work like this. You have a PV panels, and then DC-DC converter, and finally DC to AC converter, and then transformer to feed power to the grid. So this is one string, the second string. So, and you have, for each string you have a transformer, you have DC-DC converters, and you have DC to AC converters. In case of if you look at the SST solution for this application, what we can do is we can combine all these things and use modular structure. like this. So AC to DC for this, AC to DC the second one, the third string, and then we have this DC link produced by this. The solid state transformer will come here. So high frequency transformer will be part of this. And then the last thing would be to conversion of DC to AC and supplying it to the grid. So you can see, even though converters appear, but the transformer becomes smaller because it is the part of the system. Uh, this is another application which is hybrid AC to DC distribution. Now, if you have a hybrid system, then you will have DC loads, you will have charging systems, you will have PV systems. So integrating all of them into this DC bus, and you have AC loads, you have AC generation, and all of them connecting to this one AC grid. And this solid state transformer here, this would be the solid state transformer, which will connect both of them together and also integrate all of this to the grid. So grid to solid state transformer, and then to this DC microgrid, and this would be AC microgrid. Another potential application is traction. You can see in traction, we have a transformer in the locomotive, and this is low frequency transformer. And we convert this, first convert this high voltage 25 kV to around 3000 volt AC, and then rectify it, then use DC to AC inverter and feed it power to the motor and control this motor also. Now, since this converter is already there in the locomotive, we can replace this whole system with solid state transformer. What we can do is that we can directly take this catenary output, supply it, rectify it, and after rectification, we can feed it to a solid state transformer, which takes the DC input and gives DC output. And then use this final state DC to AC stage to drive the motor. And what it will do is it will reduce the size of this transformer, which otherwise this is a transformer having a rating of few MVA, and we can replace it with a smaller transformer. The power rating would remain the same. So the third aspect that I'll talk about is the topologies, key topologies for solid state transformer. So far we have looked at what solid state transformer is, and also looked at what are the potential applications. Now we will look at the key topologies of the possible topologies for developing a solid state transformer. SST development is dependent on, the SST development is, it is hinged around development of converters using wide band gap devices. Because now we have hit a situation where the further efficiency improvement in SI based devices is not possible. And we cannot enhance the efficiency further because these devices are, power rating is improved, but the device losses itself, there is no further scope, and wide bandgap devices present that scope of reducing the losses. Because when you want to, popularize this system, the converter system coming into the picture instead of simple transformer should become viable option when the efficiency is comparable. So we'll first look at the SST development with wide bandgap devices. So you can see this is a wide SiC MOSFET and GaN, they represent wide band gap devices. And you can see how these devices are placed. IGBT is here in terms of power rating and switching frequency. MOSFET is power rating is low, but switching frequencies can go up to hundreds of kilohertz. But the problem is that it cannot handle large power. Whereas SiC MOSFET present the scenario where you have both high power rating, a power rating which is much higher than IGBTs, and a switching frequency which is almost same as the SI MOSFET. GaN devices is also one other option, but GaN devices can be used only for small power application because it can go up to few kilowatts only, 4 or 5 kilowatt only. If you want to go beyond that, hundreds of kilowatt or even 200 kilowatt, you can see this would be around 500 kilowatt or so. So in that case, this device is not at all because it cannot handle those money, that much power and voltages. So now next we'll see dual active bridge topology using these devices. So this is the topology DAB. DAB is finding it's is one of the promising option for solid state transformer. So now you can see this is a DC to DC converter. So I have intentionally, we are not looking at the input side AC. If you have inputs AC grid, you can convert this to DC by using a simple rectifier. But now this transformation, the transformer part comes here in the form of high frequency transformer. So what this primary bridge will do is it will convert this DC to high frequency AC. And this will be the high frequency AC output, which will be converted to DC by secondary bridge. So it has high efficiency and bidirectional power flow. You can control the power flow from primary side to secondary or secondary to primary side by simply using a modulation, controlling the angle between the voltages, that is the voltage AB and CD. If this voltage AB is leading CD, power flow from primary to secondary. On the other hand, if CD is leading AB, power flows from secondary to primary side. And the transformer leakage reactance is used. Here the transformer leakage reactance is used for soft switching. So what we'll try to do here is, because we are operating these devices at very high frequency, and similarly these devices also. So we will try to operate these devices under soft switching conditions so that the switching loss is minimized. Or in fact, the turn-on loss is the one which forms the 90% loss of the switching loss of the WBG converters. So if we can reduce this loss, 90% of the switching loss, then 10% remaining loss can be handled. So by using soft switching, we will try to reduce the turn-on loss of these devices. So buck boost operation is possible, but each switch, the duty cycle is only 50%. So the problem with this is that one of the major issue with DAB is that when you are trying to deliver power from one side to the other side, there is always an issue there's always a small situation arising because of the voltage and currents, that there is a small back power which flows in the backward direction. So this backflow power is one of the major issues, because this will contribute into the loss of capacity of the converter, and this will also cause this will also cause reduction in the efficiency. So this back power flow is something which should be addressed. So this converter is conventionally it is using it can the modulation techniques is single phase shift SPS modulation, where this backflow power is large, then double phase shift modulation DPS, where it is reduced, and extended phase shift modulation DPS, where you have reduced backflow power as well as better quality of output voltages. So if you see with SPS you have backflow power versus the turn ratio. If this is the graph, in case of EPS it comes down to a very small value, much reduced. This is a 5 kilowatt solid state transformer, DAB based system transformer, which we have developed. It is much smaller in size. 5 kilowatt is not a it's not a huge power, but it is still quite a good amount of power. So the transformer is the whole system is dimensions are less than 1 feet by 1 feet, half feet around, all dimensions, and then you have weight also, which is much smaller. You can see here these are the waveforms of simulated waveforms, and these are the experimental waveform. You can see this V1 leading V2, and power is transferred from primary to secondary. This is the current, and you'll see this portion of the current which will cause backflow of power. So the comparison of these modulation techniques, SPS modulation, EPS, and DPS modulation. So the control variable, the flexibility, complexity. This EPS and DPS have got they're slightly more complex as compared to SPS, which is more simple. But ZBS range in case of this as SPS is limited, and ZBS range, that means have a possibility of having ZBS when the load is varying over a wide range. Then backflow large in case of SPS and low in case of DPS and EPS. Less efficiency in case of SPS, much higher efficiency in case of EPS and DPS. And power transmission range, in the first case SPS it is limited, in the second and third case it is wide. Another possibility is to have a system in which this is now a dual mode control, seamless dual mode control. What we are doing here is that we are operating mode 1 and mode 2 are used to develop the control strategy of this, and primary and secondary voltage are quasi-scale waveforms, and instead of one variable we have two variables, alpha and D, to control the system. So what we can do is, because of these two variables, we can control both backflow power as well as control the the ZBS range. So you can see this, and also reduce the peak current in the switches. So if these are the different modulation systems, the proposed one is here in the lowest one. So peak current is the lowest, even if when the power rating is increased. So two operating modes ensure that ZBS and low current stays across the devices, and the control the transition between these two modes is seamless, and junction capacitance and transformer magnetizing inductance inductances are considered in the control strategy to develop the ZVS. See, another one is DAV and LLC based single stage AC to AC. So now you see, this is a simple system, DAV based, but AC to AC. So we have AC input here, front end, this is a folding bridge or front end converter, and this is the DC link that we form, and this half bridge will be used to produce high frequency AC output here, which is applied to high frequency transformer. The secondary side also we have a bridge here, which will convert this to DC, and finally the output converter, which is unfolding bridge, which converts DC to AC. So the operation is that there is this, as per se, there is no DC link. This is a DC link, but this DC link is not using high value electrolytic capacitors. Small capacitors can be used, and you do not need to maintain a large DC link. Number one. Number two, the transformer here is, this primary side of transformer, we are using only half bridge configuration, so number of devices are reduced. And you can see here, this will be, this is the high frequency that this transformer gets. So you can see this is the input side and this is the output, which is rectified version of this. And this high frequency output is enveloped of this 50 Hz envelope only, but of changing at very high frequency. And then these devices will be operating only at line frequency, so they are not operating at very high frequency. So you get a rectified output, and this rectified output is again, unfolded using this one. So this is also, this is not a PWM type of inverter. This is a simple inverter where this rectified waveform is unfolded. So this is the specifications of DAB based single stage AC to AC SST. This was a 1.2 kilowatt experimental prototype, and the input voltage is 220 volt AC, output range is 110 to 220, and switching frequency is 25 kilohertz. Then the next one is LLC based resonant converter, single stage AC to AC SST. Now this is the input side converter with AC, input AC. You have, there is a capacitor, but these are not DC capacitors, these are AC capacitors. And these are the devices which operate bidirectional devices. So these together will form bidirectional switch, these together will form another bidirectional switch. And that means the input current can flow in both directions in these switches. So these switches will convert this 50 Hz to high frequency AC. Then we have high frequency transformer, and this is the output stage. Output stage will convert this high frequency AC to 50 Hz AC here. So this is a combined circuit of output where input AC is, high frequency AC is converted to low frequency AC. So eliminate the reverse power flow. There is no issue of reverse power flow here. Minimize the secondary current, circulating current, and achieve power flow controllability using secondary phase shift control only. See, values of these parameters, these inductors and capacitors. Small C0 is 5 microfarad. This is 500 microhenry, and these are also small capacitors. And this magnetizing inductance of transformer itself is used to create Z-wave situation. So with, we have covered some of the topologies. Now let us look at high frequency transformer. The transformer is not the normal transformer. So there is a need to look at this transformer also. So high frequency transformer, what it will do is reduce the size and weight, and high frequency transformer design has its own set of challenges. The material selection is, we cannot use the conventional core material. We have to either go for ferrite cores, amorphous, or nanocrystalline cores. And the design should be based on the material that you are using. So the ferrite core, amorphous core, or nanocrystalline core, all of them have got different uh, flux densities, operating flux densities. So depending upon which material you are implying, these materials also, cost is another factor. So depending upon the material that you are using, we should optimize we should try to reduce the losses also. Losses are in the form of core loss and winding loss, I square R loss, and skin effect loss. So all in all, there would be, these losses would become appreciable, and it is not because of the material itself, but because the size of the transformer is reduced, so cooling surface is smaller, so the thermal management or the dissipation of this heat becomes difficult. So we need to optimize the flux density, reduce the size, improve the efficiency, so that thermal management also becomes possible. So the transformer is doing, what it is doing is, it is providing isolation. It is also designed properly to create, to have a good thermal management, and size reduction, improvement in flux density, improvement in efficiency, and providing, this is important, integration of leaking inductance. So transformer leaking inductance becomes, is utilized to ensure soft switching of the converter. You can see the typical transformers. These are the 5 kilowatt transformer. You can hold them in your hand, very small size. And in fact, 100 kV transformer would be, 50 kV transformer or kilowatt transformer would be something around 1 feet by 1 feet, and 1 by 1 all dimensions. So you can achieve that. These are the core materials. And winding, winding, either we have to use the Liz wire, or we have to use a wire type of wire in the copper files. And these are Liz wire. Because they are high frequency, very high frequency, so skin effect will be pronounced. And to reduce the skin effect, we use Liz wire. And you can see this is 500 kilowatt transformer, kV transformer. This transformer, you can, if you use solid state transformer, overall the weight and volume may not reduce drastically because you will have converters also, but this system will become modular. You can handle each module separately. So, okay, with this, I'll stop. Cost is another factor, because this cost of transformer is not primarily because of the transformer only. The cost is because of semiconductor devices, the enclosures, heat sinks, filters, and electronics. So the solid state transformer cost, as I said, that cost is increased by 5 to 10 times. It is not because of the transformer material, but because of the associated power electronics. Then you have filters, you have heat sink, you have electronic control. So all these things will increase the cost. Okay, Okay, Manmohan. So I think I'll close it here.
Yes, sir. Yes, sir. That's fine. Yes, sir. Thank you. Thank you. Any questions, please? If you have any quick questions, you may ask.
Let me first see. Oh. Hello.
Sir, questions? Any questions from participants' side? Please ask.
How many participants are there? 17.
Yes, sir.
Okay, all of them online?
Yes, sir. All are online. No, participants are around 55. But like it's the official time, so maybe if you are engaged somewhere else in their accounts. So sometime more are there.
Acha.
Yes, sir. Sir, I have one question. Like this, solid state transformers are basically using the basic topologies of converter AC to DC, then DC to AC.
Yes.
So these were earlier also available. So why these, like in recent years, this attracted the attention?
Actually, these topologies were power converter topologies are there. But the point is, now time has come where we can look at these topologies delivering hundreds of kilowatts of power.
Yes, sir.
Until you bring, see, these converter topologies, what they were doing earlier, few kilowatt,
Yes, sir.
not talking about hundreds of thousands of kilowatt,
Yes, sir.
except for HVDC application. Now with the wide band gap devices, it is perceived that the converter which was capable of delivering the conventional converter, which converter of conventional size, which if delivering X kilowatt, can now deliver at least 10 times that. That means if you have 500 kilowatt converter with wide band gap devices, this can, at the same size of converter, can deliver 5 megawatt.
Okay.
And the targets are now changing. It is now penetration of power, these converters into the system, to not only deliver the quality power, but also improve the overall system. So
Yes.
your solution. For example, earlier we used to have a transformer, then all those things, and then finally you consume that power, and in the process you may inject harmonics and all those things. But right now, this solution is coming in the form of a modular solution, which is for the application. You are not burdening the distribution system unnecessarily. You take 33 kV input from 33 kilowatt kV substation, uh, put your system, and you don't need to have any further compensation. You are delivering, you are in, consuming power without burdening the system with harmonics and regulation issues.
Yes, sir. Thank you. Sir, and at one place we have connected two switches back to back for bidirectional capability. So, is it possible if diode is already there, only single switch
No,
also?
this is, this is AC input is bidirectional. Huh?
Okay.
We are not that, this is AC input. So bidirectional switch means we get positive R cycle and negative R cycle, and positive current and negative current also.
Or voltage, due to voltage also, voltage blocking capability also you want to make bidirectional.
Bidirectional.
Okay. Okay. Yes, sir. Thank you, sir. Thank you. Any questions from participants? Sir, there is no question. So I'm very much thankful to you for delivering this wonderful talk on solid state transformers. And on the behalf of EICT Academy Amenity Jaipur, once again, I thank you very much. Thank you, sir.
Thank you, Dr. Manmohan.
Thank you, sir. Okay, well, so now we will start the next session, which will be by me only. We'll continue what discussion we had in uh, afternoon sessions. So we'll take here 2 minutes break and then we'll start our session. Thank you. Anupam, are you able to see my screen?
Yes, sir.
This buck converter PI lead controller design, right?
Yes, sir.
Okay, so welcome back. Let us continue our discussion on buck converter PI lead controller design. So, in the previous session, we have so far we have discussed design part, then modeling part, then controller part, and we have seen that why controller design is important for power converters and need to regulate the voltage, right? So if we consider that we have seen in EVs, electric vehicles, and also in DC microgrid, we have a DC bus to which all the sources, storage, and loads are connected, right? And now this DC bus voltage maintain the DC bus voltage is very much necessary, right? So in order to maintain that voltage, we need to, and who will control this? This voltage is controlled by these DC to DC converters, right? So we need modeling of this, and then based upon that modeling, we need to design a controller. So the very first controller which we had designed was the PI controller, and we have tuned it using one of the good approach, that is stability boundary locus, right? Now the second, and yeah, so in that what we found that in open loop system we had some issues, like that there was DC gain, constant DC gain in the body plots of the open loop system, so due to which there was steady state error, right? First issue. Second issue was there was lot of oscillations, that was due to the poor phase margin of the system, right? So these two issues were improved by designing the PI controller. But when we designed the PI controller, the another adverse effect came into picture, that was the uh, settling time, right? Settling time was reduced. So settling time uh, should no settling time increased. Sorry, not reduced. Settling time increased, right? So increased settling time is not desirable. Settling time, we wish that it should be as less as possible, right? So PI controller helps us somewhat, but again, we need to meet the another important criteria, that is settling time, right? So settling time can be improved, and the corresponding parameter in frequency domain is the crossover frequency. So if anyhow we can improve the gain crossover frequency, and then at that gain crossover frequency we can obtain the improved phase margin, then our both purpose will be solved and our converter will give us good results, right? So this is buck converter PI lead controller design. So we will see here a new type of controller, PI lead. So you know that we have in control system we have lag compensator and lead compensator, right? Lag compensator and lead compensator. So lag compensator's special case is PI controller. It helps us to reduce steady state error, and lead compensator helps us to improve the dynamic behavior, right? So basically lead compensator adds one uh, you know adds the effect of zeros on the system, compensated system, and it improves the phase margin of the system, or you can say it adds some phase, positive phase in the system at a given frequency, right? Due to which overall system's phase margin increases and the performance improves. So let us see, this is the PI lead controller transfer function, where we have four parameter K, omega Z, alpha, and beta. So we need to tune these parameters, and alpha should be less than beta for API, for a lead function, right? This is the same transfer function, PWM controllers, PWM modulators transfer function 1 upon VSW, where VSW is 1, and this is buck converter transfer function, right? Now these transfer functions, as VSW is 1, so the GPWM is 1, so GS is the only uncompensated transfer function. Now we need to tune the parameter of PI lead controller such that we can obtain the improved performance, right? So this is how everything remains same as we discussed for PI controller, but now this error is added to the PI lead controller, and the PI lead controller's output is the modulating signal, and this modulating signal is compared with the fixed switching frequency short-tooth waveform, which in turn gives these pulses. Right now, these pulses are fed to MOSFET, and MOSFET operates. So now, if you see from outer side, the job is same, but what is getting changed? The getting changed is this VC control voltage, the way in which this error is fed. Error is, this dynamics, this dynamics is changing because this error is fed to PI lead controller. Now this PI lead controller acts on the error and gives us this modulating signal, which in turn modifies the pulse width, right? So what is the motivation, why we went for PI lead controller design, right? So we see that PI controller or lag compensator, this is the transfer function. So it is used to eliminate steady state error, but as we have seen, it introduced a phase lag. Why it is introduced a phase lag? This KPS plus KI will give a phase margin, positive phase margin, which is less than 90 degree. But this S, which is j omega, it gives a phase margin, fixed phase, sorry, it introduced a fixed phase which is minus 90. So overall, plus 90, sorry, in denominator. So overall phase which is introduced is negative, right? So this negative phase further reduces the margin. That is the only reason that it introduced phase lag in the compensator system. Therefore, it is not suitable to get good phase margin at higher crossover frequency. So what could be done? We could use the lead compensator. So here lead compensator, if you draw its pole zero plot, right? So this is sigma, this is j omega, S minus alpha, this is the location of 0, S equal to minus beta, this is the location of pole, right? But the value of beta is more than the alpha. It means your pole is located somewhere here and 0 is located here. So 0 is near to the origin. That's why the effect of 0 is more. 0 is dominating the pole, and net dominance will be of 0, right? So this is our lead compensator. But yeah, so due to this dominance of 0, the overall phase margin, overall the phase which is added to the system. So if you take the phase of this G lead of S, so K is the constant, so that will not contribute any phase, that is 0 only. And the phase which is contributed by S plus alpha, that is omega upon alpha, right? Then tan inverse omega upon beta. So if you see the overall angle, yeah. So the overall angle which is contributed at any frequency is greater than 0. So that is the positive phase is introduced. But the problem here is that if I'm going to use this lead compensator to be alone, then there is no S term here. There is no S term. So if there is no S term here, then what will happen? Steady state error will continue. Steady state error will continue. This will not be eliminated, right? So I have to have one integrator at least, right? So lead compensator is used to add positive phase at a desired crossover frequency, thus improves the phase margin. However, it does not help in eliminating steady state error. The reason is due to missing of a integrated term, right? So that was the motivation. Now, okay, so we have one more controller with us, which is PI decompensator. So one may say, okay, we can add the PI decompensator, right? Because it has integrator. But the again issue is that this integrator is having two poles in numerator, two poles. Sorry, not 2 0. numerator. So it's a 2 0 and 1 pole. So overall, if you see, it will introduce the positive phase in the system, but the reason is that due to presence of this pole at origin, it eliminates closed loop steady state error for step input disturbance to the DC to DC converter system. So that is fine. That is desirable feature. It also helps to improve phase margin. That is also fine. But what is the problem? Problem is that, however, it introduced plus 20 dB per decade slope in high frequency region, therefore making the compensated system more susceptible to high frequency noise and output voltage ripples. What it is saying? It is saying that there are two zeros. So every zero will contribute plus 20 dB per decade in slope at higher frequency. This also 120 dB per decade. Then this pole will contribute minus 20 dB per decade, right? So overall, if you see, one pole's effect will be cancelled by another zero, but one zero's effect will be there. So this is 20 dB per decade slope will be there at higher frequency. So let us consider one case. For example, let's say this was your original uncompensated system. Now you are adding in cascaded with that system this PID controller. So what will happen? It will, so let's say this is minus 20 dB per decade for the uncompensated system. Now your PID is there, so at higher frequency this will add plus 20. So what will happen? It, okay, in starting it will be like that, but later on it will become like this, right? Minus 20 and plus 20 due to this. So this is 0 dB. It means it becomes constant. It becomes constant. So what is happening earlier? This system was providing attenuation at high frequency. You can see here, and it is increasing, but due to addition of this PID controller, this attenuation has become constant, right? So at higher frequency, this will introduce the noises in the feedback path, and that will reflect in turn in the output. We will see few of the examples. So that's why this PID controller, PID compensator or PID controller, that cannot be used to achieve the crossover frequency to very high value and simultaneously getting the uh, enough phase margin, right? So that motivated us to go for PI lead compensator design, right? So what we wanted here, that we use PI compensator and we use this lead compensator. Both we will use in cascade, such that this PI compensator will help us in low frequency region to improve the gain of the system. So this is low frequency region. So such that this compensator will help us to give this initial slope of minus 20 dB per decade, and this lead compensator will help us to improve the phase margin in high frequency region. So we will separate this into two parts. So in low frequency region, my controller will be working, and in high frequency region, our lead compensator will be providing us the enough phase margin at desired crossover frequency, right? So that is the aim in our mind, and then we simplified this. But if I take this to be directly to compensator and cascade, then I have to have 1, 2, 3, 4, 5 parameters I need to design. So we did some applied some mathematics, kind of just simple mathematics. It's nothing great here. We rearrange the things, right? We rearrange the things, and we have finally, after rearranging, like k lead is taken, ki is taken, and then we rearrange the terms, and finally we obtain this pi lead compensator in this form, right? And here you can see 1, 2, 3, 4 parameters are there which need to be tuned, right? So one parameter we have eliminated. Now where this k is ki, k into ki lead, and omega z is ki kp. So I need to find k, I need to find alpha, I need to find beta. Well, so alpha is less than beta here. It is the same term as we had in alpha is less than beta in lead compensator, right? So now here K, omega Z, alpha and beta are the parameters of PI lead compensator which is to be designed, that is RM. So this is now structure of our or you can say transfer function of our new controller, which is PI lead controller. So the challenge with us is that we should tune this value of K, omega Z, alpha and beta such that it meets the desired performance specifications. So we have with us the transfer function, right? It's a second order and it's a fourth order DC to DC converter, and this will be the generalized transfer function we have taken. Now this is our compensator whose parameters we need to find. Now this is the algorithm which we have generalized algorithm which we have proposed to tune the parameters. So first, as I said, that this PI controller we will be tuning in low frequency region. So this is the part of PI, this section is the part of PI controller design. So here this omega Z I will choose very low value, right? Because I want to design it as a corner frequency for low frequency region, right? So I will choose this omega Z to be very low. Omega Z is the corner frequency of PI compensator, right? So that is the first consideration we will take. Once we have designed this omega Z, then we have our original transfer function with us, right? Now this original transfer function and this section of this controller, that becomes our new transfer function. And now for that transfer function, I need to just design this K S plus alpha upon S plus beta, right? So that's how the things goes on. So if once I choose an omega Z, then this part is known to me. So this I merge with our original transfer functions. Now this becomes my new plant for which I need to design a lead compensator, right? So because this transfer function is already having one pole at the origin, so for this, the output voltage will not have a steady state error if there is a step change. Okay, now the PI controller design, so that is done. Now PI lead this is yeah. So PI lead controller design is the function of PI lead controller is to provide the required phase margin at desired gain crossover frequency to improve the transient response. So this transfer function now we want to tune these parameters we want to calculate for given system, which is we are denoting with G1. G1 is nothing but GS into GPI. PI we have already included in that, right? So what we do first we specify that what phase margin we want to have and at what crossover frequency we want to have this phase margin. So that phi margin and omega GC we do define, right? Now we have this G1 with us, right? So what we do now, because we have defined omega GC and what is the gain crossover frequency, as I told earlier that it is 1/10 to 1/5 of, as a thumb rule, of uh, switching frequency, right? It is 1/10 to 1/5 of the switching frequency, that is the thumb rule. If you go beyond that, if someone say okay we need more and more crossover frequency, so that is better, but if you go more and more, then there will be more noises, right? So we do not go, we restrict it to 1/5 only, right? Now at this omega GC, what we do, we find the system's phase and system's gain, that how much is already available me, right? So we want the phase margin at certain frequency. Now we will see that how much is system already having, so that the remaining balance I can provide, right? So that's what we are calculating. Okay, phi 1 is with this much phase is already with me and this much gain is already with me, so remaining should be provided by the lead section, right? So to fulfill the specified phase margin and gain crossover frequency requirement exactly, the lead section parameter should be designed to contribute K required and phi required at omega GC. So now this, what is this K required? K required is the remaining gain. So if I provide a lead section provides this gain 1 upon K1 and original system is K1, so this will be getting multiplied. So what is the overall gain at omega GC? 1, and that's what we want, right? We want that at omega GC this magnitude plot should cut the 0 dB line, then only we will be able to define the phase margin, right? So it means K required should be 1 upon K1, right? Now at the same frequency omega GC, now we will see the system phase which is minus phi1. So minus phi1 plus this phase margin, right? Minus 180 degree. So this phase margin, phase is required from the lead section. This phase is required from the lead section. Then only your phase margin will be, if you simplify this again, this phase margin will be 180 degree plus phi1 plus phi required, right? So phase margin will be 180 degree plus phi1 phi required. So 180 degree is there, phi1 plus phi required is the phase, right, of the system. But this phase was not alone, it is coming after this phi required is added, right? So then only my phase margin will be phi m. So this phi required and K required has been obtained, right? Now it is the responsibility of this lead section to provide this K required and phi required, right? So we have this lead section's transfer function S plus alpha upon S plus beta. This is your G lead of S. Okay, so now you put here in this, you put S equal to J omega. So what we are getting? G lead, J omega equal to K, J omega plus alpha upon J omega plus beta. So we can get its magnitude and frequency, magnitude and phase. So the magnitude of this will be K square root of omega square plus alpha square divided by omega square plus beta square. So that is, let's say, Km. This is the magnitude at any frequency. Obviously, this is the magnitude at any frequency for this particular transfer function. And what is the phase at frequency omega? That is tan inverse, and obviously you can find from here tan inverse omega by alpha minus tan inverse omega upon beta, right? So this is the phase of this system at any frequency omega. So tan inverse omega upon alpha minus tan inverse omega upon beta. We can simplify, use the formula for tan inverse A minus tan inverse B. So we get this equation. It means at any frequency, this this lead section provides this gain and this phase, right? Well, but what we want, that at omega GC, this should provide K required and phi required. If I put omega equal to omega GC, then this value should be equal to K required and phi required, which is known to me, right? So first thing. Second thing, because this phase is provided by this lead section, but at what frequency? So if you plot characteristics by varying the omega, and if you take the phase here on y-axis, then what you will see, that this value is positive, right? But it is varying like this, it is varying like this, and at certain value of omega, this will provide maximum phase margin, and I want to capture that phase margin. And same time I want that this omega should be equal to my omega GC, at which my phase margin is maximum, and that phase margin I will equate to phi required, right? Okay, so what I did, in order to get the maximum value of this phase margin, what I will do, I will differentiate this phi lead with respect to omega and will make it to 0. So if I differentiate this, then you will see, let's say tan phi equal to omega beta minus omega upon omega square plus alpha beta. So if you differentiate it, omega square plus alpha beta, and this gives me beta only, no, beta minus alpha, then minus omega square plus alpha beta, and then differentiate omega beta minus alpha, then 2 omega, right, equal to 0. So this beta minus alpha will cancel out. So what is left? Omega square plus alpha beta minus 2 omega square equal to 0. So from here omega square comes out to be alpha beta, that is omega equal to root alpha beta, right? And this is the frequency at which the phase lead is maximum, right? Phase lead is maximum, and by putting this omega I am equal to square root alpha, we can find this value. So this value, which is the maximum value, will be tan inverse. I'm putting in this omega is root alpha beta minus alpha divided by omega square alpha beta plus alpha beta, tan inverse, right? Alpha beta, 2 times alpha beta, so 2 times root alpha beta, phi m. So this is the value of phi m. Okay, we can translate it in terms of sign if tan is known to us. So if tan means uh, this is beta minus alpha, this is 2 square root alpha beta, so we can find this one, right? We can find this is beta plus alpha, so from there we can find this sine inverse or cos inverse, whatever. So that is first term, phi m has come. Now the second, km, right? If you put here this omega m equal to root alpha beta, so what is this? K alpha beta plus alpha square upon alpha beta plus beta square. You take alpha to be common, then in denominator beta to be common, then this expression you will get k into square root alpha upon beta, right? So these three terms we have obtained: value of frequency at which maximum phase occurs, this is the value of maximum phase, and this is the value of gain provided by the lead section at the omega equal to omega m, where your phase is maximum, right? So these three things are with us also. So what we will choose, we will try to choose that this omega should be equal to my omega gc, right? This phi m should be equal to phi required, and this km should be equal to k required. So if three variables are known to me and I put it here, then 1 2 3 are unknown, that can be easily obtained, right? So that's what I'm doing. So omega gc should be equal to root alpha beta, like similarly phi required should be equal to phi and k required should be equal to km. So this frequency omega m is chosen as desired crossover frequency. Therefore the parameter phi m km must be equal to this. So now these three equations we have obtained, right? Now here this omega gc is known to me, phi required is known to me, k required is known to me. So these are known, but alpha is not known, beta is not known, alpha beta again not known, k is not known. So three equations, three unknowns. Can we simplify it? Of course, yes. Right, we can simplify it. So after simplification, right, after simplification, we get this value of k, alpha, and beta in terms of k required, phi required, and omega gc, and all these three are known to me. So if I put k required, phi required, and omega gc, then I can get k alpha and beta. I can get k alpha and beta. So now my transfer function is complete. My transfer function is complete because I in my transfer function. This was my transfer function. So k alpha beta was unknown to me, that I have obtained. Omega z I had chosen very low to the switching frequency, about 150th. So now my algorithm, with the help of this algorithm, all parameters have been obtained, right? So this is a summary. First of all, what we do, we obtain the transfer function, right? Then we design the PI section, in which omega z is the crucial parameter which we select by placing it at lower frequency. Then we merge this transfer function with converter's transfer function. Then we take it as a G1, the new plant, right? For that plant, we find at omega GC what is the phase margin, what is the K required, what is the phi required, right? Now, using these three values, we can get the value of K, alpha, and beta. In this way, we design our PI lead section. So these are the same parameters which we had taken earlier, same parameters. So then only we can compare, right? If we take the same parameters, then only we can compare the results and show whether the phase margin is improved, but whether crossover frequency is also being improved or not, right? So this is the same transfer function, putting same values, right? Now this transfer function having the same body plot, same issues, right? This is the same as we had done previously, same. So here we wanted to improve the crossover frequency as well as it's a phase margin, right? So now the question comes that how to choose omega z, and what is the phase margin should we have, how much crossover frequency we should have, how much omega z we should have. So what we did in our study, in our research, that we have taken these three values, omega z, omega GC, and phase margin, different combinations. So we fixed two at a time and varied the third one, right? So like performance analysis with variation of phase margin at constant omega z and omega GC. So what we did, phase margin we have put 30 degree, 45 degrees, 60 degree, 75 degree, and 90 degree. And corner frequency we set to be 40. And like this set we have repeated first on omega GC 0.5, then 1 kilohertz, 2 kilohertz, 3 kilohertz, 4 kilohertz, like that, right? So if we change the crossover frequency, then K alpha beta changes, then this transfer function also changes. Like if I say phi margin 30 degree, FGC 0.5, FZ 40, right? Then transfer function FZ40. So this will be our PI section and this will be our total PI lead section, right? Now we will implement this, and for like 0.5 kilohertz, all the phase margins we have plotted this gain margin and phase margin plot. So what we see here, that this phase margin increases, right? Here phase margin increases, right? When phase margin is increasing, then this is kind of frequency response, right? So as phase margin is increasing, then what is happening, you can see here this overshoot is decreasing. That's what we wanted to see. So now overshoot is decreased here also, here also, here also. Which one we should take, that need to decide. Then omega z and omega gc we have fixed, and then we change the phase margin, right? So like that we have taken various combinations at constant omega z, omega gc, and now we have taken FGC to be 2 kilohertz, right? Then 3 kilohertz, then 5 kilohertz. Like that we have taken various combination of FGC, and we have plotted and analyzed the system and recorded how this time response is behaving, right? Then what we did, we kept phi margin and omega z to be constant, and varied the omega gc, right? Varied the omega gc. So in that case also we have observed time response and its frequency response. So phase margin is fixed to 75 degree, right? And omega z is also fixed, right, to 40 hertz, and then omega gc is increased, right? So when omega gc increased, then our time response increases like that. So what we are seeing that as you are increasing omega gc, then our system is having low settling time, which is desirable, right? Low settling time, which is desirable. So it means increasing FGC is better. On the other hand, increasing uh, phase margin is also better, right? So which one we should take? Then what we did, we logged these things, that FGC to be 2 kilohertz and phase margin to be 75 hertz. And then because earlier we fixed this omega z to 40 hertz, so we have to analyze now that what is the impact of changing omega z also. So we have again changed this omega z to 10, 20. It's omega z means radian per second, fz means in hertz. So both are just different way of representing the frequency, right? So 10, 20, 40, 100 and 200. So we have taken various parameters and then we observed this settling time, rise time, etc. Then we found that what is happening, here, that overshoot is increasing, right, as soon as I am increasing the fz, right? But time is decreasing, right? Time is decreasing. Settling time is almost rise time is almost same, but settling time is decreasing, right? So if I would like to have better settling time, then I have to compromise with overshoot. But if I want to have good overshoot, better overshoot, then I have to compromise with settling time. So what we could do, we could take the some in-between solution where we have better settling time as well as better. 1.6 is not too big, right? It's manageable, right? So if one wish to go for lesser, if overshoot is important for him, then they go for fz to be 20 hertz as well, right? So based upon that, we have selected this combination 40 hertz, 75 degree, 2 kilohertz, right? And this is the transfer function for that. So we have done it through thorough analysis at various combinations, right? So what is the observations from here? That as phase margin is increased, the overshoot is decreased, right? But rise time and settling time is increased, which is not desirable. So phase margin increased, overshoot decreased. That is okay. But rise time, settling time also increases. So this feature is not better. Gain crossover frequency is increased. So frequency is increased, so definitely settling time will decrease. But overshoot is increased, so this is not right. And fz is increased, rise time, settling time decreases, but peak overshoot increases. So this is contradictory. So what best choice is given for us, that we have chosen like this. And now this, based upon these three parameters, fz 40, 5 margin 75, fgc 2 kilohertz, we comes out with this gpi lead, right? We comes out with this gpi lead transfer function, right? And now we will analyze our system with this new PI lead transfer function. Okay, so this is our PI lead, and this is red one is the compensated system, blue one is the uncompensated system, and this green one is the transfer function of PI lead. So what you will see here, for red one compensated system, if you see here, the crossover frequency is 2 kilohertz, which I wanted, and phase margin is 75 degree. So for that only we have tuned the system, phase margin to be 75 degree and crossover frequency to be 2 kilohertz, right? Now, you will see here minus 20 dB per decade slope is there. So that steady state requirement is met, right? Now phase margin is improved. So this red one, so this is the phase margin is improved, right? And this crossover frequency is also 2 kilohertz. Earlier it was very less, around 100 hertz or something like that. So all three parameters are meeting here, right? And this is why this is there, because that this omega gc, my original system, is having very poor phase, right? But this, like this much phase is introduced by this. Okay, this much phase is introduced by my PI lead controller, right? So due to this positive phase is added here, so now overall phase margin has been increased, right? And you will see here again my slope is not getting disturbed. Slope is minus 20, whatever slope it is there in existing one, that is there, right? So all features has been achieved. And when we applied this, on closed loop simulation and experiment, then we see that now this overshoot and settling time is not uh, too much, right? But in case of PI compensator, we have already seen that these overshoot and settling time was very large, right? And here also you can see that there is no overshoot and no settling time is less only, right? So same thing we have done, this input variation we have checked when load is half. Again we can see here, right? Results are better, right? Then we set VG to be constant, then change the load. So here load variation also you can see, if load is varying, then also there is very negligible variations in the output voltage. Now output voltage is set to maximum, then load is changed, so again no variation is there, right? Now I have changed the reference itself, then I could see here that this reference is also being tracked very fast. Reference is also being tracked very fast. Here also you can see, right? So what happened here, that now I am able to, obviously phase margin is 75 degrees, so I'm able to uh, reduce the oscillations, and at the same time able to have better settling time, because my crossover frequency now has been increased, right? So one may say, okay, so these results are not there, but like one may say, if I increase crossover frequency further, then system may be fast. But no, because here lead section is there, and due to this lead section, what is happening, this lead section, if you increase the crossover frequency further, then there will be a lot of noise coming to your system. Here also you can see little noise is there, right? In PI controller this was very smooth, but here little noise is there, right? So why it is happening? So if you are increasing this crossover frequency towards here, then slightly your gain, this gain is attenuation, this not gain, I should say, this attenuation is decreasing, right? This attenuation is decreasing. It means it is inviting, or it is allowing the high frequency noise to enter in the system, right? To enter in the system. So what we have learned today, that PI controller is giving good uh, good phase margin but poor crossover frequency. PI lead controller has PI lead controller. So you are there. So this PI lead controller improves our phase margin, and also we can decide what at what crossover frequency this phase margin should be there. So in that case, we are meeting both criteria. But again, if I want to improve, I want to increase this gain crossover frequency, that is not possible with this PI lead, as it will introduce the noises in the system. Therefore, we go for further advanced techniques, or we go for multi-loop converter, two-loop converter, where current control and voltage control both are there, right? So with this, we end today. And if you have any query, please let me ask. If you have any doubt, you may ask. Any query, please? Okay, so if there is no query, we stop here, and tomorrow is the last day of our FDP. So we will meeting tomorrow. I will be sending you the schedule for tomorrow, and then we will complete this FDP tomorrow. Thank you very much. Thank you. Okay, Anupam, we can stop and set the same timing for tomorrow.
Okay, sir.
Well, thank you.